Welcome to the official training curriculum for the Oracle 1z0-133 WebLogic Server 12c Administration 1 exam. In this introductory module, we will outline the architectural scope, technical prerequisites, and the systematic path to your professional certification. This is an unofficial, independently produced educational resource. It is not affiliated with, endorsed by, or connected to Oracle Corporation in any way. All trademarks, including Oracle and WebLogic, belong to their respective owners. If you are looking to validate your skills as a middleware professional, this course provides the most direct route to mastering WebLogic 12c. We strip away the unnecessary noise and focus precisely on the core domains required to pass the exam and manage enterprise environments effectively. By the end of this journey, you will possess a rock-solid understanding of system topologies and complex application lifecycles that define the modern Oracle middleware stack. This is your foundation for building highly available, secure, and scalable Java EE deployments. Our curriculum follows a logical progression designed to mirror the actual exam blueprint, beginning with fundamental infrastructure architecture and moving through to advanced security hardening. We will navigate the intricacies of domain creation, administrative tool usage, and the often misunderstood nuances of the node manager. You will learn to manage server lifecycles, configure dynamic clusters, and fine-tune JDBC connection pools for high-performance enterprise applications. Each module is built to ensure you are not just memorizing answers for the test, but acquiring the operational competence demanded in real-world production data centers. To succeed, you must approach this material with a mindset focused on precision and technical correctness. As administrative tasks require exact configuration steps, we will. Welcome to the Architecture module, where we will build the foundation required to master the WebLogic infrastructure for your certification. By the end of this chapter, you will possess a professional understanding of domain topologies and the structural boundaries that define enterprise-grade application environments. To understand the architecture of WebLogic Server 12c, we must first establish the concept of a domain as the primary unit of management. A domain is a logically related set of Java EE components, including resources like data sources, JMS servers, and the application instances themselves. At the heart of this domain sits the administration server, which serves as the central control point for the entire configuration. This server does not typically run business applications, but rather provides the administration console and the Java management extensions interfaces used for orchestration. All changes to the configuration, whether performed through the console, the command line interface, or WLST scripts, are serialized into the config.xml file residing in the domain's home directory. This centralization ensures that your entire infrastructure remains synchronized and consistent, which is a critical requirement for maintaining high availability in production environments. When scaling our infrastructure, we transition from the administration server to managed servers, which are the actual workhorses of the ecosystem. These managed servers are instances that host your deployments, such as web applications, enterprise beans, and web services. While they reside within the domain and share the global configuration managed by the administration server, they operate independently as separate JVM processes. This separation of concerns is fundamental to the architecture because it allows you to isolate the management plane from the execution plane. Even if a managed server experiences a failure or heavy load, the administration server remains operational to facilitate monitoring and administrative intervention. You organize these nodes into logical groupings, often referred to as clusters, to provide redundancy and scalability across multiple hardware resources. The concept of a machine in WebLogic terminology acts as a logical linkage between the software environment and the physical or virtual hardware. A machine does not represent the server process itself, but rather the underlying host address where one or more server instances reside. This abstraction is vital because it allows the node manager to remotely restart managed servers on a specific physical host if they become unresponsive. By correctly mapping your managed servers to these logical machine entities, you enable the platform to be aware of the hardware topology. This awareness is particularly effective in virtualized environments or cloud deployments, where the mapping allows for smarter load balancing and failover strategies. Without this logical boundary, the WebLogic domain would lack the necessary context to perform intelligent health monitoring across heterogeneous hardware layouts. Our structural analysis must also account for the directory skeleton that defines how the domain lives on the file system. Every domain possesses a specific home directory containing the configuration data, security files, and current deployment state. Within this structure, you find the bin directory for domain-wide scripts, the servers directory for individual instance runtime data, and the security folder for managing key stores and credentials. Understanding this layout is not merely an academic exercise, it is a practical necessity for troubleshooting configuration drift or performing manual backups and restores in a production scenario. The directory structure follows a predictable pattern regardless of the operating system, ensuring that your operational knowledge remains transferable across different server environments. This rigid organizational approach ensures that the lifecycle of every component is contained and manageable through both manual file system access and automated tooling. Finally, we look at the network layout and the boundaries imposed on the infrastructure runtime. When designing these systems, you must ensure that the communication pathways between the administration server and its managed servers are secure and performant. This involves configuring network channels that define specific ports and protocols for different types of traffic, such as administrative operations versus application throughput. You are essentially creating a virtual network fabric on top of the physical infrastructure, which dictates how components interact with external clients and each other. By maintaining these strict architectural patterns, you minimize the surface area for configuration errors and simplify the complexity inherent in distributed Java environments. This discipline is exactly what the examination requires, as it tests your ability to think in terms of coherent, scalable, and manageable system topologies. I look forward to our next deep dive into the installation process. Welcome to the chapter on WebLogic Server software installation, where we will master the deployment of the server binary across various enterprise environments. In this instruction, we will cover the technical transition from installation binaries to a fully operational software footprint. When approaching the installation of Oracle WebLogic Server 12c, it is crucial to understand that we are dealing with a Java-based middleware engine that requires a precise operating system context to perform optimally. Before executing the installer, you must ensure that a certified Java development kit is already present on the host system, because the installer itself is a Java archive that relies on the system runtime. The generic installer is the industry standard for production environments because it allows for a decoupled installation process that remains consistent across Linux, Unix, and Windows platforms. You should check the Oracle certification matrix to confirm that your chosen OS version and kernel patches align with the specific 12c minor release. Establishing a dedicated Oracle user account with correct file system permissions is not just a security best practice, but a functional necessity to prevent conflicts during the extraction of files. Proper directory layout planning, such as keeping the Oracle middleware home distinct from the domain home, will simplify your maintenance tasks significantly in the future. Once the directory structure is finalized, you must verify that your environment variables, specifically Oracle Home and Java Home, are correctly exported in the shell profile. This preparatory work forms the backbone of any stable middleware installation and prevents the cryptic errors that often surface during the domain creation phase. The interactive graphical user interface mode is the most common starting point for administrators who are performing a fresh installation or verifying the installation workflow on a new development server. By running the jar file using the Java command, you trigger the installer's engine, which performs a series of prerequisite checks against your system's memory and disk space before presenting the welcome screen. The GUI provides a guided path through the selection of the installation location, the choice of standard versus complete installation profiles, and the initial dependency scans. While this is intuitive for those familiar with Oracle products, it is important to remember that the GUI is merely a layer on top of the underlying command line implementation. You should observe the progress bars carefully to ensure that the inventory files are written correctly, as these files are what Oracle's global inventory daemon uses to track your patches and component versions. If the GUI fails to launch due to an X11 forwarding issue on remote servers, it is a clear indicator that your display environment variables or local tunnel configurations are not sufficient for visual interaction. In such cases, or when security or volume dictates, moving to an automated command line approach is the natural technological evolution. Transitioning to silent mode installation is a requirement for enterprise-scale deployments where consistency and reproducibility are mandatory for operational success. You achieve this by creating a response file that acts as a blueprint for the installer, dictating the installation location, security settings, and inventory pointer information without requiring human intervention. This text-based parameter file must follow a strict key value format that the installer uses to bypass the graphical prompts entirely. You run the installation command with a specific flag that points to this response file and an inventory pointer file, signaling the engine to execute the tasks programmatically. This method is incredibly powerful because it eliminates the potential for human error inherent in clicking through long installation wizards across dozens of servers. Once the command completes, you should always verify the contents of the Oracle inventory directory to confirm that the installation was registered correctly within the central registry. If the registration fails, administrative tools like the Oracle Universal Installer or subsequent patching tools will not be able to recognize the presence of the product. Automated silent installations also allow you to log all output to a file, which serves as a vital audit trail for compliance and troubleshooting purposes. Software patching and maintenance are inseparable from the initial installation, and the Oracle OPatch utility is the primary lens through which you will manage these binary updates. OPatch works by applying specific patches to your already installed Oracle home, and it requires that the environment be in a quiescent state, generally meaning the servers should be stopped. Before applying any patch, you must check the README file provided with the Oracle Patch Bundle, as it highlights specific prerequisites and potential conflicts with existing components. The mechanics of patching involve the tool comparing the file versions in your middleware home against the patch metadata to determine if a replacement is necessary. It is a best practice to always create a backup of your entire Oracle home before kicking off any patching procedure, as this allows for a fast rollback in the event of an unexpected incompatibility. Once the patch is applied, you should revalidate the installation by checking the inventory again to see the updated version stamps and any newly applied patches listed. Keeping your installation metadata in sync with the actual binary state is the mark of a disciplined administrator, as this ensures your 12c environment remains both secure and fully supported by Oracle technical support. See you in the next lecture. Welcome back. In this chapter, we will explore the procedural mechanics of constructing custom WebLogic domains to establish robust administrative boundaries for your enterprise applications. If you are looking to master the foundational infrastructure of Oracle WebLogic Server, this chapter is essential for your success. We will transition from theoretical concepts to the practical application of building production-ready domains that form the backbone of your middleware environment. By the end of these lessons, you will possess a complete understanding of how to architect, deploy, and replicate domain configurations across your organization's footprint. This course is designed to turn complex administrative requirements into predictable, repeatable outcomes, ensuring you are fully prepared for the certification examination. In this lesson, we will focus on the creation of custom domains using the Oracle Configuration Wizard, which serves as the primary automated vehicle for domain initialization. When you initiate this process, you are essentially defining the directory structure and the underlying configuration files that the WebLogic runtime relies upon to function. You have the choice to start from scratch using vanilla templates or to leverage specialized industry templates that pre-configure specific integrations like service-oriented architectures or enterprise portal components. The wizard abstracts away the tedious task of manually editing XML descriptors by generating them for you based on your input parameters. I find that starting with a well-defined template is superior to manual construction because it minimizes the risk of structural inconsistencies that can haunt your environment later. Always ensure that the destination file system path is isolated from the product installation directory to maintain a clean separation between binaries and domain states. Beyond the basic domain structure, the initialization process allows you to define the core elements of your topology, such as the administrative server parameters and the managed server topology. You need to consider how your physical machines will map to these logical constructs, especially when planning for high availability or load-balanced environments. During the initial setup, identify your target dynamic managed server specifications to ensure that the environment can scale horizontally without requiring a fundamental redesign later on. Base clustering structures, while they can be added later, are infinitely easier to manage when configured during the initial creation phase via the wizard. Think of this phase as the blueprinting step where you define the connectivity and authentication mechanisms for the domain administrator. It is important to remember that these initial settings define the scope of your console interactions and the visibility of managed targets within the administrative domain. Once you've established a domain, you will often find the need to replicate or move that domain state into different network segments or testing environments. This is where binary packing and unpacking command line utilities become an indispensable part of your toolkit. By utilizing the pack utility, you can compress a domain into a template archive that preserves all the specific settings, including security configurations and resource definitions. You can then use the unpack utility on a remote node to reconstruct the domain accurately, maintaining consistency across distributed hardware distributions. This approach effectively eliminates configuration drift, as you're not manually recreating variables, but rather deploying an identical state to every node. It is a reliable, idempotent way to ensure that your development, staging, and production environments align perfectly according to your predefined architectural standards. See you in the next lecture. Welcome to this module, where we embark on a thorough exploration of the various administrative interfaces and management frameworks that define the daily operational experience within WebLogic Server. You are going to master the fundamental tooling required to manipulate complex domain configurations efficiently and reliably. In this chapter, we focus on the practical navigation and functional analysis of the WebLogic administrative ecosystem, specifically targeting how you interact with the configuration subsystem. We will bridge the gap between the intuitive browser-based administration console and the programmatic power of the WebLogic scripting tool, or WLST. WebLogic relies on a centralized management infrastructure, and understanding these tools is not merely about knowing where to click, but about internalizing the transactional nature of how the server stores and validates its state. By the end of this module, you will understand how to transition from manual ad hoc configuration to automated consistent management, which is a prerequisite for passing the exam and succeeding as a production engineer. These skills are the foundation for every other administrative task you will perform in an enterprise environment. The WebLogic Administration Console serves as the primary gateway for most operators and is built directly on top of the management session framework. When you log in, you are essentially establishing a transient management session that allows you to traverse the managed beans or mbeans that reside within the administration server. The console provides a structured hierarchy that reflects the logical composition of your domain, including servers, clusters, and deployed applications. It is important to realize that the console is an abstraction layer, meaning every action performed through the web browser ultimately results in a modification to the underlying configuration files, such as config.xml. To maintain integrity, WebLogic enforces a strict change management architecture that prevents conflicting modifications. When you begin to edit settings, you are effectively initiating a transactional process that requires you to lock the configuration, apply your desired changes, and then activate the pending modifications. This change management architecture is non-negotiable and fundamental to the stability of an enterprise server. When you attempt to change an attribute, the system places the domain into an edit mode, creating a separate workspace for your session that remains isolated from the active runtime configuration. This isolation ensures that other users or administrators cannot unexpectedly disrupt your workflow while you are in the middle of a complex update. Once you have made your changes, you must validate them, which triggers a series of consistency checks to ensure that the new values conform to the domain schema and business requirements. Only after you click the Activate Changes button are those modifications pushed to the runtime. It is a transactional model that mirrors principles found in database management, where atomicity and consistency are prioritized above all else. This process is essential because it prevents partial configurations from corrupting a server instance. Complementing the graphical interface is the WebLogic scripting tool, which is a command line interface based on the Jython interpreter. While the console is excellent for visualization, WLST is the indispensable tool for automation and environments where repeatable deployments are required. You can operate WLST in two primary modes: interactive, where you type commands directly into a shell, or script-based, where you execute self-contained files. Within WLST, you navigate the mbean tree similar to a file system, allowing you to examine attributes and execute operations programmatically. This is particularly useful for tasks like bulk configuration of data sources or adjusting server parameters across dozens of managed servers simultaneously. Relying solely on the console is limiting, as scripting allows you to incorporate version control and unit testing into your architectural lifecycle. Mastering the command line approach is often where the most significant administrative efficiencies are gained. Beyond simple configuration, you must also be capable of tailoring the administration environment to suit your specific operational needs. The console allows for various preferences, such as modifying how information displays across tables or controlling the visibility of contextual documentation. You can effectively manage a multi-user environment by utilizing persistent session tracking, which ensures that administrative actions are properly attributed and audited within the domain logs. It is also common to adjust certain functional behaviors, such as disabling specific help features or adjusting how often the console refreshes its internal state. These might seem like cosmetic changes, but in a high-pressure production environment, a customized console can significantly reduce the cognitive load on an administrator during an incident. The key is to recognize that administrative preferences are stored per user, allowing for a personalized management experience that doesn't impact the actual domain configuration. See you in our next session. Welcome back to our exploration of the WebLogic Server infrastructure. In this lesson, we will examine the configuration and implementation of the Node Manager utility to enable effective server lifecycle automation. Node Manager acts as a Java-based agent that runs as a separate process from the WebLogic Server instance, providing the necessary separation of concerns required for robust lifecycle management. Its primary architectural value lies in its ability to start, stop, and restart managed servers on behalf of the administration server, even when that administration server is temporarily unavailable or unreachable over the network. By shifting the responsibility of process monitoring and lifecycle control to an entity that resides locally on the target machine, we reduce our dependency on a single point of failure. When you deploy the Node Manager, you are effectively introducing an autonomous oversight mechanism that survives the crash or restart of the primary administrative console. The utility communicates through an encrypted channel, ensuring that management signals are transmitted securely across your distributed environment. This architectural choice is essential for high availability, as it automates the recovery of managed servers following hardware failures or unexpected process termination. Understanding how to wire this utility into your existing domain is a foundational requirement for any robust production deployment. The heart of the Node Manager's configuration is the Node Manager Properties file, a profile that dictates how the agent behaves and interacts with the host operating system. Within this file, you define the listen address and the unique port number that the agent will use to accept incoming management commands from the administration server. Security is clearly a primary concern here, as we must define the key stores and identity certificates to facilitate SSL communication between the administration server and the Node Manager. You can further customize the utility's behavior by enabling custom scripts that allow the engine to execute specific shell commands during a stop sequence, which is particularly useful for cleaning up legacy resources or external dependencies. There is also the health pole interval, a parameter that specifies how frequently the Node Manager probes the status of the managed servers in its care. If your systems are prone to intermittent network instability, tuning this value prevents the agent from prematurely assuming a process has failed. Furthermore, you must configure the crash recovery settings to dictate how the utility should respond if it detects an orphaned process or a stalled server instance. Physical enrollment is the manual but critical process of associating a specific machine definition within the administration console with the physical server running the Node Manager instance. This enrollment bridges the logical configuration of your topology with the reality of your underlying hardware and network addresses. You create a machine object in the WebLogic console, assign it a listen address and port, and then ensure that the Node Manager on the target host is configured to trust the administration server's identity. Once this handshake is successful, the administration server can send commands to the Node Manager, which then manifests as start or status requests locally on that machine. When you initiate a start request from your centralized console, the Node Manager verifies that the domain directory is accessible and then spawns the Java process for the requested managed server. This remote orchestration effectively abstracts the complexity of server administration, allowing you to manage a global set of instances via a single administrative interface. Monitoring the status of these remote servers is equally streamlined, as the agent continuously streams heartbeat data back to the console to reflect the current runtime state. As you begin to implement these configurations, pay close attention to the file permissions of the node-manager.properties file and the associated startup scripts. It is a common point of friction to find that the node manager process lacks the necessary system privileges to execute the server startup command on behalf of the WebLogic user. Consistency across all your machines is paramount, so I recommend defining a standard directory structure for your node manager installations to simplify your baseline monitoring. If the agent does not report a server status correctly, the first step is usually to examine the local NoHoop or log files generated by the node manager process rather than relying solely on the UI. These logs provide a clear audit trail of every interaction, including authentication failures and script execution errors, which are notoriously difficult to debug from the administrative console alone. Keep your security settings tight, ensuring that only mandated management traffic can access the node manager port, as this port effectively functions as an administrative gateway to your infrastructure. With these settings in place, your WebLogic environment moves from a collection of loosely managed processes toward a cohesive, resilient ecosystem ready for production. I will see you in the next lecture. Welcome back. In this chapter, we will explore the lifecycle states of a WebLogic server instance and the mechanisms required to manage them effectively. Understanding the server lifecycle is foundational to maintaining high availability and predictable system behavior. When we talk about a WebLogic server instance, we are referring to a state machine that transitions through distinct operational phases. The server begins in a shutdown state, where no resources are active. Upon initiating the start process, it enters the starting phase, during which the JVM initializes, the configuration is loaded, and the essential internal subsystems are brought online. Once the services are ready to accept connections with restricted access, the server reaches the standby state. From there, it can transition to the admin state, where administrative operations are permitted, but application traffic is not yet allowed. The final operational goals depend on the transition to a running state, where the server is fully engaged in servicing requests. Transitions are rarely instantaneous, and the engine relies on intermediate phases like resuming and suspending to ensure state safety. The resuming phase occurs when a server moves from an admin or standby state toward the running state, indicating that application pools and listeners are being activated to handle user traffic. Conversely, the suspending state is an essential orderly shutdown mechanism that allows the server to finish processing active requests before it stops accepting new ones and eventually powers down. Should an unrecoverable error occur, such as a critical subsystem failure or an exhaustion of internal resources, the server enters the failed state. Understanding these state transitions is crucial for diagnosing why a server might be stuck in a non-productive mode. Monitoring tools provided by the Administration Console or WLST allow you to query these states programmatically and trigger transitions when necessary. Beyond the standard lifecycle, managing the server environment requires deep familiarity with the initialization process, including scripts and environment configurations. The startup sequence relies on variables defined in the bash or shell profiles of the host operating system, which dictate the Java home and domain locations. Fine-tuning the JVM memory footprint is a daily task for an administrator, as improper XMS and XMX values can lead to severe performance degradation or immediate crashes during the startup cycle. These parameters are often passed as arguments within the managed server's start scripts or via custom class path additions that incorporate third-party libraries needed by your applications. If you modify these scripts, you must ensure that the shell environment remains consistent across all nodes to avoid discrepancy errors. Configuration lock conflicts often arise when multiple administrators attempt to modify the domain structure simultaneously, preventing the server from transitioning states while the edit lock is held. Troubleshooting startup failures requires a systematic approach to identifying where the initialization engine stalled. A frequent culprit is an invalid security certificate or an expired key store, which prevents the server from binding to SSL ports during the initiation handshake. You should always inspect the server logs, specifically the STEDOUT and the diagnostics logs, which will pinpoint whether the failure occurred at the JVM level or within the WebLogic subsystem layer. Disaster recovery at the server level often involves utilizing the node manager to automate restarts on alternate target systems if a local instance cannot be recovered. However, automatic restarts must be carefully configured to prevent flapping, where a server continuously restarts in a loop due to a persistent configuration error. By mastering these components, you ensure that the server infrastructure remains resilient against both software glitches and human-induced configuration errors. See you in the next lecture. Welcome back. In this chapter, we explore how to architect robust network topologies in WebLogic Server by mastering network channels and traffic segregation. When we talk about WebLogic network channels, we are fundamentally discussing the abstraction of communication protocols from the underlying physical network interfaces. By default, a managed server binds all traffic to a single port and network interface, which is rarely sufficient for production environments that demand isolation. Network channels allow us to define multiple access points for a single server instance, effectively decoupling the administrative control plane from the data plane consumed by end users. You might need to segregate traffic so that heavy external HTTP requests do not saturate the capacity reserved for intercluster replication or administrative heartbeats. This segregation is achieved by configuring custom channels that specify different bind addresses, ports, and protocols such as T3, T3S, HTTP, or HTTPS. Once defined, these channels serve as independent entry points, ensuring that critical operations remain responsive even when the primary application ports are under heavy load. A critical component of this advanced configuration is the domain-wide administration port. If you have ever experienced an unresponsive administration console due to an application-induced thread pool exhaustion, you understand the necessity of this feature. The administration port acts as a dedicated, private channel specifically for administrative traffic, such as deployment operations, configuration updates, and server monitoring. When enabled, this port mandates that all administrative actions occur over a secure channel, effectively isolating the control logic from standard application traffic. You must exercise caution, however, because enabling the administration port prevents the managed servers from starting unless they can successfully connect to the administration server through this dedicated path. It essentially creates a management silo that guarantees reachability during periods of extreme network congestion or high traffic volume. Beyond simple port segregation, network channels provide granular control over the protocol behavior itself. For example, if you are running an internal replication service, you might want to force that traffic to utilize a specific channel configured with a non-blocking TCP behavior, while keeping public-facing HTTP traffic on a different channel optimized for client browsers. These channels permit you to set distinct timeout values and connection queue limits, which prevents a slow client on one network interface from propagating performance degradation to internal processes. We can bind these channels to specific interface addresses on the host machine, which is particularly useful in multi-home server environments where we want to keep internal management traffic on a private VLAN while exposing application services to an external load balancer. This approach naturally extends to the concept of virtual hosts, which allow us to map specific URL patterns or host names to target isolated application instances residing within the same WebLogic domain. Virtual hosts act as a sophisticated routing layer that sits atop your network channel infrastructure. By defining a virtual host, you provide the WebLogic internal HTTP server with the logic required to direct incoming requests towards specific web applications regardless of the target server's physical identity. This is a common requirement when you need to host multiple distinct applications on a shared managed server while presenting unique domain names to the outside world. When you combine virtual hosts with network channels, you create a very precise delivery mechanism, where specific URL requests are filtered through dedicated channels that impose their own resource constraints and protocols. It is this level of control that transforms a standard WebLogic deployment into a production-grade infrastructure capable of handling high-throughput traffic and specialized security requirements. To implement these features effectively, you must understand the interplay between the channel configuration and the server's listen address settings. When you create a network channel, it overrides the default listen port configuration for the specific protocols defined, but the server container retains its default listener as a fallback. It is often wise to explicitly configure a specific bind address for every channel to prevent the JVM from inadvertently listening on all available network interfaces, which is a common security oversight. In more complex scenarios, you might implement edge routing where the channel settings facilitate a handshake with external hardware load balancers that perform SSL termination before forwarding the request into your managed server. Keeping these configurations consistent across a cluster is essential for smooth replication and inter-server communication, particularly when managing session persistence in geographically distributed sites. See you in the next lecture. Welcome back to our deep dive into the Oracle WebLogic Server 12c. In this lesson, we will explore the mechanisms involved in creating and managing traditional server clusters to ensure your enterprise applications remain available and performant under load. When we talk about traditional clusters in WebLogic Server, we are essentially discussing a group of managed servers that work together to provide increased scalability and reliability for our applications. Unlike newer dynamic cluster architectures, traditional clusters are defined by static membership, where each managed server must be explicitly configured and associated with the cluster group beforehand. This design requires a deliberate approach to the physical or logical placement of your JVM instances across your hardware infrastructure. We typically want to spread these instances across multiple physical machines to prevent a single point of failure from taking down the entire service. By grouping these servers, we create a unified front where the system can handle higher concurrency than a single server instance ever could. The administrator must balance this effort by carefully considering the resource requirements of each JVM, ensuring that we do not over-provision the host machines. Proper planning starts with the definition of the communication protocols that these nodes will use to synchronize session data and health status. The actual provisioning process usually begins within the configuration wizard when we initially set up the domain, though it is just as common to modify an existing domain via the WebLogic administration console. Once you have navigated to the environment section in the management interface, you can designate specific managed servers to be members of your cluster. A crucial aspect here is the concept of application targeting, where we define exactly which deployed components will run on which servers within our cluster architecture. For example, if you have a suite of enterprise Java beans or complex web applications, you can target them to the entire cluster, ensuring that every member is running that code. This distributed execution is how we achieve the load balancing effect, as the cluster proxy then distributes incoming client requests across the chosen nodes. When a user sends a request, the cluster-aware proxy knows which nodes are active and capable of receiving traffic, helping to hide the underlying complexity from the end user. This setup effectively transforms a collection of individual server instances into a powerful, cohesive computing fabric. However, deploying code is only one part of the equation because high availability also requires robust state management, especially regarding transactional integrity. As we scale out our applications, we must configure advanced transaction management properties, particularly those related to the Java Transaction API. When servers operate within a cluster, the transaction coordinator must be able to track and resolve global transactions even if one participant in the cluster goes offline during the process. This is where persistent transaction logs come into play, as they act as a safeguard to ensure that the system can recover to a consistent state upon restart. In a traditional cluster, these transaction logs are typically stored in a file-based system or in a dedicated database store, depending on your performance requirements and the architecture of your underlying storage. If you rely on the default transaction store, the system writes these logs to the server's local file system by default. But in a production environment, you should consider moving these to a shared, highly available storage location. Failing to manage these logs correctly can lead to fragmented transactional states, which makes the recovery process significantly more complex after an unexpected node failure or system outage. To facilitate these transactional guarantees, each server instance within the cluster needs to be configured with the appropriate T-log settings, which are internal indicators used during the recovery process. The administrative duty here involves verifying that every managed server in your traditional cluster has a designated, accessible path for these logs that won't become a bottleneck during peak periods of activity. Furthermore, when dealing with enterprise applications, you must ensure that your session data management or session replication is synchronized with the cluster's specific transaction settings. While the application handles the business logic, the infrastructure layer, as represented by WebLogic Server, remains responsible for the durable recording of the operations taking place. Think of this as the difference between writing transient data and ensuring the ACID properties are preserved across distributed physical nodes in a data center. By meticulously configuring these components, we build a foundation that supports the unpredictable demands of high concurrency systems without sacrificing the integrity of the information being processed. See you in our next technical discussion. Welcome back. In this session, we will examine the mechanics of dynamic clusters, providing you with the technical foundation to implement elastic scalability within your WebLogic environments. Traditional clusters in WebLogic Server necessitate manual intervention for every server instance added to the topology, which involves configuring individual managed servers, assigning them to machine abstractions, and manually mapping network listeners. This administrative overhead becomes a significant burden when your infrastructure requirements scale rapidly in response to volatile application demand. Dynamic clusters solve this problem by decoupling the server configuration from the individual server instances themselves. Instead of defining each server, you create a server template that acts as a blueprint for all members of the cluster. When you define a dynamic cluster, the administration server uses this template to derive properties like Java arguments, resource limits, and port offsets mathematically based on a dynamic server limit. This approach ensures consistency across your environment, as every clone inherits the same baseline configuration, thereby eliminating the configuration drift that often plagues large, static deployments. The core of this architecture relies on the concept of server templates and calculated attributes to define the behavior of the cluster. When a dynamic cluster is created, you specify a maximum number of servers that the cluster is permitted to host, and WebLogic reserves the necessary configuration slots for these potential instances. You then apply a server template, which allows you to define a property once and have it propagated to all members without redundancy. Attributes that need to be unique per server, such as listener ports or server names, are managed through calculated expressions. For instance, you can instruct WebLogic to generate a listen port by taking a base port value and adding an index representing the current server's position in the cluster. This abstraction allows you to scale your footprint from a few nodes to dozens with minimal administrative interaction, as the infrastructure handles the instantiation of these properties automatically at runtime. Beyond simple instantiation, dynamic clusters provide a sophisticated framework for assigning servers to specific hardware resources using machine naming patterns or network subnet rules. In a standard setup, you manually map a managed server to a machine object, but with dynamic clustering, the system uses assignment policies to distribute workloads across your distributed infrastructure. By utilizing machine name string aliases or subnet-based filters, you can ensure that instances are automatically placed on the appropriate physical or virtual hosts as they are provisioned. This is especially useful in environments where high availability mandates that specific cluster members reside in distinct fault domains or geographic data centers. By defining these policies up front, you allow the WebLogic domain to make informed placement decisions without requiring a human administrator to micromanage the assignment of each individual JVM process. Elasticity is the primary reason for adopting this model, as it enables your environment to grow or shrink in response to real-time workload requirements. Engineering these scale-up and scale-down procedures involves interacting with the dynamic cluster's capacity, effectively toggling the number of active servers within the boundaries you establish during the initial configuration. Since the dynamic instances share a common configuration template, the overhead of spinning up a new node is significantly lower than introducing a brand new server definition into the domain. You must, however, be mindful of the underlying hardware constraints and the performance impact of rapidly adding or removing nodes, as the cluster itself requires a stable topology to maintain health checks and load balancing integrity. By matching your active server count to the current application traffic, you maximize the efficiency of your infrastructure investment while maintaining the strict certification standards required for stable, enterprise-grade production clusters. I will see you in the next lesson. Welcome back. Today we examine the mechanics of implementing cluster proxies to establish a robust front end for your WebLogic deployments. In professional production environments, exposing managed servers directly to the public internet is rarely a sound architectural choice. Instead, we typically position a dedicated Oracle HTTP server, or OHS, as a reverse proxy tier to shield our internal resources. By utilizing the Oracle Web Tier Installer, we gain access to the specialized modules required to bridge HTTP requests from the perimeter to our internal cluster members. This configuration essentially creates a highly resilient load balancing layer that acts as the primary point of entry for client traffic. When we deploy OHS in this capacity, we are essentially offloading the burden of connection management and request distribution away from our WebLogic middleware layer. This decoupling allows the application servers to focus exclusively on executing business logic rather than negotiating low-level socket connections with external entities. It is an architectural pattern that improves both security and scalability within the enterprise landscape. The actual integration logic resides primarily within the middleware module, which must be correctly configured to interface with your backend cluster. The core of this configuration hinges on the modifications made to the middleware.conf file, where you define the specific directives that dictate how traffic is routed. You will need to define the WebLogic cluster directive by providing a comma-separated list of the managed server addresses and their corresponding ports. Furthermore, the WebLogic host and WebLogic port parameters serve as the default routing behavior if the cluster-wide directive is insufficient or needs a specific target. Beyond the addressing scheme, you will often find yourself managing timeouts to ensure that a hanging backend process does not indefinitely exhaust your front-end capacity. Careful tuning of these directives is necessary to maintain a balance between responsiveness and system stability under varying load conditions. When a request arrives at the Oracle HTTP server, it must be translated and forwarded using specific rules that govern request distribution. The standard mechanism here is a round-robin algorithm, which effectively spreads the incoming load across the participating nodes in the cluster. However, it is important to observe how connection failover behaviors initiate when a node becomes unresponsive during a transaction. If one of the managed servers in the cluster fails to respond within the defined threshold, the module attempts to retry the request on another available node. Depending on the state of the session and the configuration of your persistent markers, this failover can often occur transparently to the end user. You must ensure that your proxy configuration aligns with the session replication strategy you have established for the cluster members themselves. Without this alignment, a proxy might try to route a stateful request to a server that lacks the necessary context to complete the transaction successfully. The translation mechanics involve not just path-based routing, but also the preservation of critical header information during the proxying process. As the OHS handles the request, it adds headers such as the WL proxy client IP to ensure the backend servers have visibility into the original client metadata. This level of transparency is essential for security auditing and for any application-level logging that depends on identifying the source of an incoming request. You should also consider the idle timeout and connect timeout parameters as primary levers for hardening your proxy tier against network-level disruptions. By setting these values appropriately, you ensure that stalled internal processes do not cause a bottleneck at the edge tiers. Failure to manage these connection parameters correctly is a common source of instability in high-traffic deployments where cluster performance is paramount. Always document your proxy directives clearly, as troubleshooting issues in this layer often involves correlating timestamps across multiple different log sources. If you notice imbalances in load distribution, verify your round-robin implementation by analyzing the access logs generated by the OHS. While it is tempting to view the proxy tier as a simple pass-through mechanism, it is in fact an active participant in maintaining the integrity of your WebLogic cluster. A well-configured reverse proxy is the difference between a resilient, highly available enterprise system and one that is fragile in the face of minor network fluctuations. You should aim to minimize the complexity of your routing rules while maintaining enough granularity to support the specific needs of your applications. This balance is what defines a truly mature administration practice for the WebLogic platform. See you in the next lecture. Welcome back. In this lesson, we will focus on the fundamental mechanisms used to ensure session persistence across WebLogic server clusters. When we construct highly available architectures, the primary challenge is maintaining stateful information across multiple application server instances. In WebLogic, this is achieved through HTTP session replication, which moves current user session data from one server to another as cluster members participate in a shared state environment. Without this mechanism, a user whose session is bound to a managed server would lose their entire application context if that specific server instance were to become unavailable or undergo a restart. The architecture relies on designating a primary server that holds the session object and at least one secondary server that acts as a backup storage point for that same object. When an HTTP request arrives, the load balancer or the proxy plugin directs the traffic, and the server infrastructure ensures that the session state remains synchronized between the primary and the replica. This process involves a distinct communication cost, as every creation, update, or invalidation of a session necessitates an update to the secondary server to ensure that the backup remains consistent with the current state. To gain finer control over where this data resides, we employ the concept of replication groups. By default, WebLogic attempts to place a secondary session on a different server within the cluster than the primary. However, in larger deployments spanning multiple physical machines or geographic racks, simply choosing a different server instance is often insufficient to guarantee true fault tolerance. Replication groups allow you to explicitly define preferred secondary locations by grouping managed servers, ensuring that the secondary session is hosted on a completely different machine or at least a different physical rack. You configure these groups within the cluster settings by assigning each managed server to a specific replication group and defining a list of preferred secondary groups. This approach mitigates the risk of a single chassis or power supply failure, affecting both the primary and the secondary session copies simultaneously. It is an exercise in capacity planning where we balance the overhead of network traffic against the requirement for physical redundancy. When we examine the actual data movement through communication pipelines, we encounter the reality of replication latency. The replication process is inherently network-bound, meaning that the speed at which secondary session state is updated depends largely on the underlying network topology and bandwidth available between cluster members. If your environment uses in-memory replication, the cluster uses IP multicast or unicast to communicate state changes throughout the cluster member set. You should be aware that excessive session size or high frequency of session attribute updates can saturate these communication channels, leading to perceivable performance degradation for end users. Administrators often need to monitor the replication statistics provided in the WebLogic console to identify bottlenecks in these pipelines. Optimizing the network payload involves assessing whether there is redundant information being pushed to the secondary server and adjusting the session persistence configuration accordingly to minimize administrative traffic. Testing these configurations requires us to simulate failure scenarios to verify that the failover logic actually triggers as expected. You cannot claim that a system is high availability compliant based solely on configuration files. You must prove that the state is recovered when a primary node vanishes. This typically involves initiating a load test, forcing a controlled shutdown of an application server node, and observing if the client's subsequent request is routed correctly while retaining the previous state. During these scenarios, you should monitor the server logs for any replication-related exceptions or errors in session synchronization. If the secondary server does not promote itself to primary correctly, you might be facing an issue with the replication group's member list or the network channel configuration. By carefully analyzing the behavior of the session stickiness versus the session replication, you can distinguish between a failure in the load balancer proxy and an actual deficiency in the cluster's ability to recover state on the secondary instance. I will see you in the next lecture. Welcome back to our technical journey through WebLogic server infrastructure. Today, we turn our attention to the internals of cluster communication and how we effectively troubleshoot the networking layer that binds our managed servers together. At the heart of any Oracle WebLogic cluster lies the necessity for reliable server-to-server communication, which is orchestrated primarily through a heartbeat mechanism. When a cluster functions correctly, every managed server regularly broadcasts its state to its peers, ensuring that membership information remains consistent across the entire domain. Historically, this relied heavily on IP multicast, where packets were sent to a specific group address. However, modern environments often struggle with multicast due to network infrastructure limitations or restricted routing policies. Consequently, unicast has become the preferred transport mechanism because it leverages a point-to-point mesh configuration. In a unicast setup, the lead managed server acts as a central hub for heartbeat data, which significantly reduces the noise on the network compared to the chatter of an open broadcast channel. Understanding this distinction is vital because troubleshooting requires us to know whether we are dealing with a mesh of individual connections or a shared broadcast medium. When we observe connectivity issues, we often encounter the dreaded split brain scenario where the cluster divides into two or more isolated segments. This usually happens when the heartbeat timeout threshold is exceeded, causing nodes to perceive their peers as unreachable, even when the physical hardware is operational. We must scrutinize the heartbeat interval settings and the failure detection periods within the cluster configuration to diagnose if the tuning is too aggressive for the current network latency. If you suspect packet loss, you should verify the network interfaces using command line utilities like netstat or TCP dump to capture the actual traffic flow. Monitoring the WebLogic server log files is equally critical, as they will contain specific signatures identifying connectivity drops or repeated reconnections. Look for markers indicating cluster partition events, which provide clear evidence that a node was ejected or failed to verify its presence within the established heartbeat window. To address these challenges, the administrative console allows us to configure custom replication channels that prioritize cluster traffic over standard application requests. By isolating this traffic, we can ensure that heartbeat signals are not queued behind heavy user workloads, which is a common cause of false positive node failures. These custom channels can be assigned to different network interfaces, effectively creating a dedicated path for administrative and cluster-specific packets. When configuring these environments, you must also evaluate the performance dashboards provided by the WebLogic Diagnostic Framework. These tools offer a real-time view into the health of the messaging pipeline, providing metrics that correlate heartbeat latency with overall system performance. If the dashboards indicate sustained spikes in transmission time, it is an immediate indicator of network congestion, which requires bandwidth throttling or traffic reprioritization at the OS level. Resolving complex partition issues often requires a methodical approach of verifying infrastructure before altering software configurations. Start by isolating whether the issue is transient or persistent by correlating timestamps from the server logs with any known spikes in network utilization. In cases where packet drops are identified as the root cause, updating the cluster heartbeat frequency or adjusting the failure threshold can bridge the gap, but this should only be done after validating the network layer. Ensure that the administration channel is properly set up, as this provides a fallback mechanism for the server to communicate status during periods of high load. By maintaining awareness of the distinction between unicast peer-to-peer and multicast broad-spectrum configurations, you gain the diagnostic clarity required to stabilize demanding cluster deployments. Always prioritize the collection of diagnostic data from all affected nodes to identify the specific point of failure within the communication stack. I will see you in the next lecture. Welcome to a new exploration of the WebLogic Server ecosystem, where we focus on the fundamental mechanics of application provisioning. In this lesson, we will dissect the lifecycle of Java Enterprise Archives and the administrative mechanisms used to transition code from your development environment into a running runtime instance. To understand deployment in WebLogic, we must first look at the structural anatomy of the standard Java Enterprise Edition archive formats. At the lowest level, we have the Web Archive, or WAR file, which encapsulates web components like servlets, JSPs, and static assets alongside their specific web deployment descriptors. Moving up the complexity ladder, we encounter the Java Archive, or JAR file, which typically maintains enterprise Java beans and service-oriented classes intended for reuse. The pinnacle of this hierarchy is the Enterprise Archive, or EAR file, which serves as a container that bundles these WAR and JAR archives into a single, cohesive unit of execution. Every well-formed archive relies on standard deployment descriptors, such as web.xml or ejbjar.xml, which define the contract between the application code and the underlying container. By strictly adhering to these standards, we ensure that our applications remain portable across various compliant servers, including the WebLogic runtime. Understanding these containers is the prerequisite for moving from simple file placement to true enterprise-grade provisioning. Once we have our archives prepared, we must utilize the administrative frameworks provided by WebLogic to move them onto our target servers. The WebLogic Administrative Console provides a graphical interface that is often the starting point for most administrators, as it allows for intuitive verification of target servers and individual cluster members. Beyond the GUI, the WebLogic Deployer tool remains a staple for CLI-driven automation, enabling you to integrate deployment activities directly into your shell-based build scripts. Furthermore, WLST or the WebLogic scripting tool, offers a programmable Python-based approach that allows for complex, conditional deployment logic that survives infrastructure changes. When moving packages from a source repository, you must be precise about the target scope, whether that involves a single managed server or an entire cluster boundary. These tools encapsulate the heavy lifting of communicating with the administration server, which then propagates the deployment artifacts to the relevant nodes in your domain. Consistency in your tooling strategy is generally a reflection of the stability of your underlying environment. Deployment process within a WebLogic domain follows a rigorous lifecycle that transitions an application through several distinct states. Initially, the process begins with preparation, where the server validates the archive and its descriptors to ensure that the environment can support the application requirements. Following preparation, the distribution phase occurs, which involves the physical copying of the bits to the target server's local staging directory or a globally shared location. Once the files are securely in place, the activation step occurs, effectively loading the classes and resources into the JVM and marking the application as ready to receive traffic. If an emergency arises or a configuration change is required, you can move an application into a suspended state, which prevents new requests while allowing current transactions to finish gracefully. Finally, the undeployment process cleanly removes the application, ensuring that references are pruned from the server's configuration and that disk space is reclaimed. Managing these transitions manually is rarely recommended, as the scripted approach guarantees that you never omit a cleanup step in your server runtime. See you in the next lecture. Welcome back. In this chapter, we will examine the mechanics of distributing application archives across a multi-node WebLogic domain environment to ensure efficient deployment. When we deploy applications in a WebLogic server cluster, we face the fundamental challenge of ensuring that every managed server has access to the application binaries. The staging mode determines how these files are physically distributed across your infrastructure. By default, WebLogic uses stage mode, where the administration server acts as the source and copies the application archive from its known path into the staging directory of each targeted managed server. This directory resides locally on the file system of the host machine running the managed server. This approach is generally robust because it reduces the reliance on external network availability once the deployment process is complete. If the connection between the nodes were to face latency or temporary downtime, the managed server continues to function because it is executing from its local copy of the application. However, this creates a situation where the binary is duplicated many times across the cluster, which might be inefficient if you're dealing with very large enterprise archives or limited disk space. If your architecture relies on a centralized storage solution, such as a high-performance network-attached storage array or a shared file system accessible by all nodes via a network file system mount, you should consider utilizing no-stage mode. In this configuration, the managed servers do not copy the application archive locally. Instead, they read the application files directly from the source path provided during the deployment process. You must ensure that the path is identical and accessible from every single node in the cluster, as a failure to resolve the file path on any specific managed server will result in a deployment failure. This mode is particularly advantageous when you frequently update large applications, as it avoids the time-consuming process of copying files across the network during every deployment cycle. You avoid the overhead of administrative file copying, but you essentially trade that for a requirement of high availability and performant shared storage. If your storage backend experiences congestion, the application start times will likely suffer as all nodes contend for read access to the same shared location. External stage mode provides a third alternative for environments where you want to maintain control over the distribution process using custom scripts or external tools. In this scenario, WebLogic Server does not attempt to distribute your application files automatically, nor does it necessarily look to a shared mount for the source. You are responsible for ensuring that the application bits are manually placed in a specific, predictable directory on every target node before you initiate the deployment command in the administration console or via WLSD. This is often the preferred choice in highly automated continuous integration pipelines, where configuration management tools such as Puppet, Chef, or Ansible are in charge of distributing binaries to the fleet. It allows you to integrate deployment distribution with your existing infrastructure provisioning workflows. While it requires more setup and manual synchronization, It gives you absolute control over the version of the bits residing on each node, ensuring that no unexpected automatic copying occurs during a rolling update. Choosing the optimal staging mode is a balancing act between network bandwidth, storage throughput, and the operational cadence of your team. If your deployment frequency is high and your archives are massive, the network traffic generated by stage mode might become a bottleneck during peak hours. In such cases, moving to no stage mode on a high-speed storage fabric is usually the correct architectural evolution. However, remember that no stage mode implies that an outage of your storage layer is equivalent to an outage of every single WebLogic managed server that depends on it. External stage mode is useful for decoupling your deployment process from WebLogic internals, especially when you need to perform staging operations during specific maintenance windows or using proprietary deployment protocols. Before you decide, observe your existing deployment duration, check the available I/O throughput on your storage devices, and consider the complexity of your current automation scripts to determine which path provides the most stability for your specific domain topology. I will see you in the next lecture. Welcome back to the course. In this lesson, we will explore the mechanics behind WebLogic deployment plans and how they enable environment-specific configurations. When we deploy applications to production, we often face the challenge of different environmental requirements for systems that are otherwise identical in terms of logic. A Java Enterprise Archive file is generally meant to be immutable, meaning you should not unpack it to change a configuration file and repack it every time you move from a testing environment to a production instance. This is where deployment plans step in as a mechanism to externalize configuration details that vary between environments. By utilizing an XML-based descriptor stored outside the archive, we can define overrides for deployment properties while leaving the original binary untouched. This separation of concerns allows the operations team to manage environmental drift without needing the source code or build artifacts from the development team. From an architectural perspective, this is a clean way to ensure that your application binaries remain consistent across the entire software delivery lifecycle, which is a foundational requirement for any stable enterprise deployment strategy. A deployment plan is essentially a blueprint that instructs the WebLogic server on how to modify the deployment descriptor settings during the application installation or update process. When you generate a base plan, you are creating an XML file that captures variable definitions that reference existing deployment descriptors like web.xml or the WebLogic application.xml files within your archive. Once this plan is applied, WebLogic merges the settings from the plan with the settings in the archive binaries, resulting in an effective configuration used by the running instance. You might use this mechanism to point your application toward a local database URL in a staging environment while simultaneously pointing it to a clustered high-availability database connection string for your production environment. By creating distinct deployment plans for each target, you avoid the common pitfall of shipping environment-specific credentials or network addresses inside the application package itself, which is a major security and management concern. Navigating the administration console reveals the practical side of manipulating these configuration parameters. When you initiate the deployment process, the console provides an interface to define custom property overrides, such as resource references, JNDI names, or specific tuning flags like pool capacities. As you adjust these values in the console, WebLogic can dynamically save these modifications into an external plan file that you can store in your version control system or deployment automation repository. This approach is superior to hard-coding values because it treats the configuration as part of the infrastructure state rather than part of the application code. Furthermore, if you need to upgrade an application, you simply deploy the new archive while pointing to the existing, stable deployment plan, ensuring that your environment-specific settings are applied correctly to the new version without manual intervention. Managing multi-environment target schemes requires a disciplined approach to how you version and store these plans. If you are responsible for multiple environments, you should establish a convention where each environment has a corresponding deployment plan that mirrors its specific requirements, such as unique server targets or security configurations. You can then automate the deployment process using scripting tools like WLST, which accepts the path to these external plan files as an argument during the deployment command. This systematic approach guarantees that the transition from a quality assurance phase to the production stage is predictable and repeatable. It reduces the likelihood of human error during configuration updates because the plan acts as the single source of truth for all changes that deviate from the defaults defined inside the packaged application. With this methodology, you ensure that the WebLogic domain remains clean and that the lifecycle transitions are handled with the level of precision expected in professional enterprise administration. Until we meet again. Welcome back. Today, we are moving beyond basic deployments to look at advanced redeployment techniques. In this lesson, we will focus on zero downtime strategies and managing multiple application versions within the same WebLogic domain. In professional environments, the classic approach to redeployment, where you simply replace the old files with the new ones, is often insufficient because it disconnects existing user sessions. To avoid service disruption, WebLogic Server provides the production redeployment feature, which allows two versions of the same application to coexist in the same domain. When you deploy a new version with a specific version identifier configured in the deployment descriptor, WebLogic marks the new version as active for all incoming requests. Crucially, any user already interacting with the older version continues to be served by that specific version until their session expires or they finish their current task. This isolation ensures that you do not force a hard cutoff on your users, which is essential for maintaining a positive user experience during maintenance windows or feature rollouts. The mechanism driving this behavior relies on WebLogic's ability to maintain separate class loaders for different versions of the same application. When you initiate a production redeployment, the server registers the new version while keeping the old one in a retired state. In-flight requests are handled by the retired version, while all new initial requests are routed to the new version automatically. This routing logic is built into the WebLogic server infrastructure, meaning the transition happens seamlessly without requiring changes at the load balancer or the network layer. Once all active sessions for the legacy version have timed out or completed, the server automatically unregisters the retired version, freeing up the allocated memory and resources. This graceful handover is the hallmark of modern enterprise application lifecycle management. While production redeployment is elegant, you must manage certain complexities, particularly regarding shared resources and static dependencies. If your application relies on shared libraries, updating those libraries can trigger conflicts if the new application version is not compatible with the older library version still required by the retired application instance. Often, you may need to update shared static files, such as images or style sheets, which are usually hosted globally. When you modify these shared components, you have to be careful not to break the retired version that expects the original structure. In practice, this often means your deployment plans must account for these shared assets by versioning them if necessary, or by ensuring the application code is decoupled from the specific version of the static resources. In situations where you cannot perform a full production redeployment, you might resort to in-place updates, though this typically involves more risks. In-place strategies are often used for minor patches where the application logic and session structure do not change significantly. However, even with minor updates, class loader conflicts can arise if you change dependencies within the application archive. WebLogic uses distinct class loaders for each module and application, and attempting to hot deploy changes while sessions are active can sometimes lead to inconsistent states if the application state is persisted in memory objects that are no longer compatible with the new code. Always verify the deployment descriptor settings, specifically the application version identifier, to ensure the container knows exactly how to handle the transition between the bytecode versions, as these identifiers are the source of truth for the container during the staging and deployment process. See you in the next lecture. Welcome back to our exploration of WebLogic server deployment strategies. In this section, we examine the deployment of shared Java Enterprise Edition libraries to optimize your server's resource consumption. We will focus on how to decouple common utility classes and shared frameworks from your primary business applications, allowing them to remain independent. Shared libraries represent an architectural decision to move common code outside the application artifact, such as an EAR or WAR file. When you deploy these libraries independently, you reduce the physical size of your business applications and promote a more modular structure within the WebLogic ecosystem. This modularity is not merely a convenience, it serves as a mechanism to manage memory footprints efficiently across multiple application instances. By isolating common frameworks into these shared layers, The server container avoids loading redundant classes, which directly translates to lowered permgen or metaspace usage depending on your Java version. The beauty of this approach lies in the separation of concerns, where the lifecycle of the infrastructure code is managed distinctly from the lifecycle of the business domain code. Configuration of these libraries begins at the metadata level within the archived files. Specifically, you must configure your manifest MF file to include the necessary extension name and specification version attributes. These attributes are not optional metadata but active instructions that the WebLogic class loader uses to resolve dependencies at runtime. When you package your library, ensure that these headers strictly adhere to the expected naming conventions, as even a minor mismatch will result in a deployment failure when the system attempts to link the library to the consuming application. The application, in turn, references these shared resources by declaring the same extension name and version constraints in its own manifest file. This two-way handshake ensures that the container can perform validation before the application ever attempts to instantiate its first class. Targeting and deployment of these modular software layers follows a workflow similar to standard application deployment, though it requires a different mental model. You first deploy the library as a global or scoped resource, ensuring it is targeted to the appropriate managed servers or clusters that represent the runtime environment. Once the library is registered, WebLogic effectively elevates it to a shared class path that acts as a parent to the application-specific class loaders. Because the library exists independently, you can update it without necessarily triggering a redeployment of all dependent applications, provided the signature of the code remains compatible. This capability is vital for organizations that maintain large-scale frameworks, as it reduces the administrative overhead associated with emergency hotfixes or minor library version increments. Maintaining system stability requires meticulous management of these explicit version dependencies and runtime class paths. If you attempt to deploy an application that requests a version of a library that does not exist in the target domain, WebLogic will halt the deployment process, preventing a runtime failure that would be far harder to diagnose. You must leverage the WebLogic Administration Console to monitor and track which applications are currently referencing specific library versions. Regularly auditing these references is a professional responsibility, as it prevents the accumulation of stale assets that consume disk space and complicate the class path configuration. By treating your shared libraries as immutable, versioned contracts, you create a robust environment where upgrades are predictable rather than chaotic, ultimately leading to a more resilient production infrastructure. I will see you in the next lecture. Welcome back. We are now moving into the phase where we verify that our deployed applications are not merely reachable, but genuinely operational within the production runtime. Testing deployed applications is a fundamental discipline in WebLogic server administration, and it serves as the ultimate bridge between intent and reality. You have already learned how to stage and deploy artifacts, but successful deployment is only the first step in a lifecycle that demands constant validation. A server that reports a success status for a deployment might still be suffering from silent failures, such as misconfigured endpoint routes or broken persistence dependencies. Our goal here is to establish a robust framework for post-deployment validation that leaves no room for ambiguity. By confirming the health of system containers and the validity of response signatures, you ensure that the end-user experience aligns with your architectural design. We will focus on both built-in console utilities and external load generation tools to provide a comprehensive look at how an application behaves under various real-world conditions. This approach allows you to move beyond basic uptime monitoring and into true performance assurance, which is essential for maintaining a stable enterprise environment. The quickest way to verify basic connectivity after a deployment is by utilizing the built-in test utilities available directly within the WebLogic Administration Console. Once an application is deployed and distributed across your managed servers, the console provides mechanisms to test the web context by invoking specific endpoints. You should navigate to the Deployment tab, select your target application, and utilize the built-in testing link to ping configured application paths. This action verifies that the container has correctly mapped the servlet context and that the interface is returning the anticipated HTTP status codes. It is a vital check for identifying issues related to context routing, request dispatching, or missing library dependencies that might only surface when the application is actually exercised. While this does not act as a full-scale integration test, it serves as an immediate sanity check that significantly reduces the time spent troubleshooting fundamental configuration errors after deployment. Moving beyond basic connectivity requires a shift toward load testing, where we evaluate how the container manages concurrent traffic and resource utilization. Tools like the Grinder console allow us to simulate real user behavior by defining scriptable scenarios that hit specific application endpoints under controlled stress. When you subject your managed server to concurrent load, you get the opportunity to observe how the container handles thread allocation and connection queuing. This is the stage where you verify that your cluster proxies are correctly distributing traffic and that session replication is holding up under the pressure of multiple active sessions. Observing the system under load also provides insight into whether your configured staging modes and deployment plans are optimized for horizontal scalability. If the container begins to show signs of instability during these tests, it is almost always an indicator that your thread pool settings or memory heap configurations require refinement. Monitoring runtime performance metrics is equally critical to the overall validation strategy, as it provides the numerical data necessary to justify your configuration tuning. You should track servlet execution speeds, as these clearly signal whether the application logic is being bottlenecked by inefficient code or slow database transitions. Furthermore, pay close attention to garbage collection frequencies, as an excessive number of full garbage collections often correlates with a memory footprint that is too aggressive for your designated JVM heap settings. Active thread allocations within the WebLogic server should be monitored to ensure you are not reaching exhaustion points during peak throughput. By correlating these physical metrics with the load testing results, you can determine if your application is effectively utilizing the underlying resources. Mapping these curves over time helps you establish a baseline, identifying what represents normal behavior versus performance degradation before it impacts your users. I will see you in the next lecture. Welcome back. In this lesson, we will examine the architectural foundations of the WebLogic JDBC subsystem and how it facilitates database connectivity for enterprise applications. At the core of the WebLogic JDBC architecture lies the abstraction provided by data sources, which decouple application code from specific database details. When an application requires a database connection, it does not communicate directly with the database driver. Instead, it performs a lookup against the Java Naming and Directory Interface, or JNDI tree. This directory service acts as the central registry where WebLogic binds data source objects so that they can be retrieved by their configured JNDI names. The request flows from the business logic layer into the naming service, which returns a reference to a data source object tailored to the application's requirements. This connection management layer maintains a pool of active physical connections to the underlying database, preventing the overhead associated with establishing a new socket connection for every single transaction. By leveraging these connection pools, WebLogic enhances scalability and resource utilization within the JVM and across the distributed environment. The internal layout of this subsystem is composed of specific driver types dictated by the requirements of the database vendor and the expected operational behavior. WebLogic supports Type 4 JDBC drivers, often referred to as thin drivers, which are written entirely in Java and communicate directly with the database using its native protocol. These drivers are generally preferred in WebLogic environments because they require no native client libraries on the server host, simplifying maintenance and ensuring platform independence. Furthermore, the architecture accommodates XA-compliant drivers for scenarios where distributed transaction processing is a requirement. These drivers implement the two-phase commit protocol, allowing the global transaction manager to coordinate atomic changes across multiple heterogeneous data sources or resource managers. Understanding the distinction between standard connection flows and these transaction-aware drivers is a prerequisite for architects tasked with ensuring data integrity in complex multi-tiered applications. Integration with the broader WebLogic infrastructure is achieved through resource management policies that govern how these connections are refreshed and validated. When a connection is reserved from a pool, the system can perform predefined test queries to ensure that the physical link to the database is still viable before handing it off to the application context. This health monitoring is integrated into the server's lifecycle, allowing the management console to visualize resource usage in real time. If the architecture is configured for distributed transactions, the WebLogic Transaction Manager oversees the interaction between the application and the resource manager, logging state transitions to ensure recovery in the event of a failure. This orchestration ensures that even in highly concurrent environments, the application remains shielded from the complexities of thread synchronization and socket management within the database connectivity layer. Balancing these settings, such as pool size, capacity increments, and timeout values, is the fundamental task of a WebLogic administrator ensuring adequate throughput. See you in the next lecture. Welcome back. In this section, we shift our focus toward the JDBC subsystem and the practical mechanics of establishing database connectivity within your WebLogic domains. When we talk about generic data sources in WebLogic Server, we are describing the standard, foundational method for providing database connectivity to our applications. A generic data source acts as a factory for database connections, maintaining a pool of ready-to-use sessions that the server manages on behalf of the deployed applications. To initiate this process through the administration console, you navigate to the Services node and select Data Sources under the JDBC submenu. Here, you define a name for your data source and provide a JNDI name, which is the specific path by which your application will look up the resource in the naming service. Choosing a descriptive JNDI name is a best practice, as it provides a clear abstraction layer between your code and the actual database physical connection details. Once these identifiers are set, you must select the appropriate database driver type based on the vendor implementation you are utilizing. The driver class name is an essential piece of metadata that instructs the WebLogic class loader on how to translate your Java code into protocol-specific database commands. The connectivity URL is the next mandatory configuration, acting as the specific endpoint address for your database instance. This URL typically follows a strict format, often dictated by the JDBC driver vendor, that encapsulates the host, port, and service name, or SID, for your target database. After providing these parameters, you are prompted to input the administrative credentials, such as the database username and password, which the connection pool uses to authenticate against the database instance. These credentials are encrypted within the domain configuration files to prevent exposure. After defining the base connectivity, the final deployment step involves selecting the target scope. You have the flexibility to target the data source to an individual managed server or to a cluster. When you target a cluster, WebLogic propagates the data source configuration to all members of that cluster, ensuring that every server instance has its own local pool of connections defined by these shared parameters. Initial testing often reveals common pitfalls that arise during the creation of these resources. If you encounter a failure during the test connection phase, the most frequent culprit is an incorrect driver class name, or a mismatch between the driver on the class path and the configuration settings. Additionally, connectivity dropouts are often symptomatic of network-level security rules, such as firewalls blocking the traffic on the specified database port or expired credentials that fail the authentication handshake. Another common issue is the failure of the JNDI binding, which usually occurs if the data source fails to initialize during the server startup phase. Always verify your logs if the data source state is not marked as active immediately following creation. By systematically checking each parameter, driver, URL, credentials, and target, you can eliminate these obstacles and establish a stable bridge between your middleware and your persistent data layer. See you in the next lecture. Welcome back. Let us examine the intricacies of tuning JDBC connection pools to ensure your WebLogic environment remains both performant and resilient. Database connection pools are essentially caches of physical database connections that allow applications to reuse existing connections rather than incurring the overhead of repeatedly opening and closing them. Proper capacity planning is the first step in ensuring that your application does not experience contention under load. You define the initial capacity to set the number of connections that the server creates upon startup, which typically should be sufficient to handle your baseline traffic without forcing the server to grow the pool immediately. Maximum capacity acts as your absolute ceiling, preventing the pool from exhausting database resources or port limits, but setting this too low can lead to hung threads as requests wait for an available slot. Between these bounds, you configure an increment value that dictates how many connections are added to the pool when the demand exceeds the current supply. allowing for a controlled rather than chaotic scaling behavior. Choosing these values requires a deep understanding of your application concurrency model and the typical latency of your database interaction, as an overly aggressive growth setting might lead to transient spikes in memory usage that could trigger garbage collection cycles. Simply maintaining an open connection is often insufficient because intermediate network devices or database firewalls might silently drop idle connections, leading to deadlocks or broken pipes when the application attempts to reserve a stale handle. To mitigate this, WebLogic provides robust health preservation mechanisms, starting with the ability to test connections on reserve, which validates the integrity of a connection right before it is handed to the application. While this is the most reliable method for ensuring application stability, it does introduce a slight latency penalty on every checkout, so it is often better to complement it with periodic background testing. By configuring a test frequency period alongside a dedicated SQL test statement, such as a simple select one from dual for an Oracle database, the connection pool proactively verifies its members while they are idle. This background scavenging process ensures that when your application finally requests a connection, the pool already knows whether it is healthy or if it needs to be replaced, effectively shifting the cost of failure detection away from the critical execution path of your service requests. Balancing resource consumption against application response requirements often involves careful management of timeout and cleanup parameters to ensure the system gracefully recovers from spikes and failures. A connection leak can easily occur if code fails to explicitly close resource objects, and WebLogic enables detection by settings that track how long an application holds a connection. If the duration exceeds the defined limit, the system can log the stack trace of the offending caller for post-mortem analysis. When the demand subsides, you rely on the shrink frequency and shrink interval to release excess connections back to the database, which prevents your application server from selfishly holding onto resources that other components or systems might require. Furthermore, fine-tuning the statement cache at the connection pool level can significantly reduce the CPU overhead on the database server by allowing the JDBC driver to reuse parsed execution plans for repeated SQL queries. Every one of these knobs and switches interacts with others, meaning that configuration should be treated as an iterative process guided by actual telemetry data collected during load testing rather than generic best practices. See you in the next session. Welcome back. Today, we are exploring the configuration of grid-linked data sources within the WebLogic Server environment. When we shift our perspective from a standard database to an Oracle Real Application Clusters environment, the traditional approach to managing connection pools often becomes a bottleneck. An active grid-linked data source essentially functions as a sophisticated, event-aware bridge between your WebLogic managed servers and the ONS, or Oracle Notification Service. Unlike a generic data source that relies on periodic polling or stale connection testing to identify failures, GridLink subscribes to fast connection failover events. This architectural integration allows the data source to react instantly when a specific database node becomes unavailable. By leveraging this reactive model, we eliminate the latency typically associated with the timeout periods of traditional test-on-borrow configurations. You are effectively shifting the burden of cluster awareness from the application server's polling logic to the database infrastructure itself. This ensures that the application tier always maintains a valid view of the available database instances within the grid, which is critical for high availability systems. The configuration process begins at the domain level, where you define the grid-link profile by providing the necessary Oracle rack listener information. You must specify the ONS configuration, which allows the server to receive real-time notifications about the status of the cluster nodes. During the setup, you will define the connection properties that identify the scan listener virtual IP and the local ONS port, which facilitates the communication protocol between your WebLogic tier and the RAC clusters. Once the connection is established, the data source starts listening for events related to node crashes or listener failures that the rack environment broadcasts. When an event signifies that a node is down, the data source proactively abandons or clears the associated connections before the application ever attempts to use them. This is a fundamental departure from typical connection pools that would otherwise attempt to hand off a broken connection, resulting in a stack trace for the end user. Proper configuration of these notification parameters is what enables the high-speed failover capabilities that GridLink is known for in enterprise environments. Beyond simple failover, we must concern ourselves with runtime connection load balancing and affinity-based optimizations. In an Oracle RAC environment, it is not enough to simply spread connections randomly across nodes, as doing so may ignore the benefits of instance-aware routing. WebLogic provides session-based and transaction-based affinity, which effectively keeps a unit of work connected to the same RAC instance for the duration of a business process. By maintaining this affinity, you reduce the overhead of cross-node data blocks and cache fusion, which can significantly improve performance in write-intensive applications. Implementing this requires you to correctly map your data source properties to support the Oracle JDBC. Oracle driver, which understands the complexities of the cluster's internal state. You should also pay close attention to the security parameters, ensuring that the connection pool uses the appropriate credentials that are granted access to all nodes within the RAC cluster. When the network configuration is tuned to handle these cross-tier protocols effectively, the overall reliability of your database interactions increases substantially. I will see you in the next lecture. Welcome to this segment where we explore the practical implementation of multi-data sources within the WebLogic ecosystem. We will discuss how to orchestrate high-availability data access by grouping multiple generic connection pools into a single logical abstraction. In many enterprise environments, a single database instance is often insufficient to guarantee the uptime requirements expected by high-traffic applications. To solve this, WebLogic provides the multi-data source concept, which acts as a registry wrapper for several underlying generic JDBC data sources. When you configure this component, you are essentially defining a high-level abstraction that hides the complexities of individual connection pool management from the application layer. Instead of the application interacting directly with a specific pool, it requests a connection from the multi-data source, which then routes the request based on the configured algorithm. This design pattern ensures that your database interactions remain decoupled from the physical topology of your environment, allowing for cleaner infrastructural maintenance and better scalability management over time. The routing behavior of a multi-data source depends heavily on the failover and load balancing profiles you choose during the configuration process. When you select the failover algorithm, the system attempts to satisfy requests by utilizing a primary data source and only shifts to a secondary backup target if the primary node fails. This is a critical pattern for scenarios where you want to maintain strict affinity to a primary database engine while maintaining a warm standby for emergencies. Conversely, configuring an active load balancing distribution allows the runtime to scatter database access across multiple engines simultaneously. By distributing the load, you prevent any single database instance from becoming a bottleneck, provided that your underlying connection pools are sized and tuned to handle the aggregate throughput required by your application. Effective configuration requires careful attention to the pool recovery algorithms that dictate how and when WebLogic attempts to reuse a failed data source. When a node in your pool becomes unreachable, the multi-data source marks it as unhealthy, preventing further attempts to borrow connections until the health checks succeed. You must configure these thresholds wisely, balancing the sensitivity of the detection mechanism against the risk of flapping, where a node rapidly cycles between healthy and unhealthy states. Monitoring the operational integrity states of these underlying components is necessary to ensure that your failover logic does not inadvertently hide systemic issues from your monitoring dashboards. If the recovery process is too aggressive, you risk overloading a database engine that is already struggling to recover, thereby exacerbating the very problem you intended to mitigate. In implementing these configurations, you must remember that the multi-data source is not a magic solution that eliminates the need for proper database management or performance tuning. Rather, it is an administrative layer that provides a unified interface for achieving redundancy and balancing traffic across distinct physical pools. By leveraging these legacy configuration styles correctly, you provide the runtime with a robust mechanism for managing connectivity in the face of partial system degradation. It is helpful to visualize this as an abstraction layer that isolates your application business logic from the volatility of the physical data access tier. Keep in mind that as you introduce more nodes into your multi-data source registry, the complexity of your troubleshooting process for connection-related errors will naturally increase. See you in the next segment. Welcome back. We are now focusing our attention on how to effectively monitor database resources within a WebLogic environment. When we manage JDBC data sources, our primary objective is to maintain a healthy and efficient link between our application layer and the underlying database. In the WebLogic Administration Console, the Monitoring tab for a selected data source provides a real-time pulse of your connection infrastructure. You should focus on metrics such as the current number of active connections and the total number of connections currently in the pool. Examining the waiting request count is equally important because it directly signals whether your pool size settings are sufficient for the current application load. If you consistently observe a high number of waiting requests, it typically indicates that your pool is exhausted, forcing threads to block until a resource becomes available. This is a common performance bottleneck that can be diagnosed by correlating these console statistics with the application response times reported by end users. Beyond simple connection counts, we must scrutinize deeper performance indicators like the average wait time and the connection pool leak incidence. A connection leak occurs when an application retrieves a connection from the pool but fails to return it explicitly through a close operation, effectively shrinking the available capacity over time. WebLogic provides instrumentation to track these leaks by monitoring the usage history of connections checked out from the pool. Monitoring the statement cache hit ratio is another fundamental aspect of database resource health, as a high hit ratio directly reduces the overhead of parsing SQL statements on the database server. If you notice a low hit ratio, it is often a sign that the statement cache size is set too low for the specific query patterns of your deployed applications. By adjusting these parameters, you ensure that the server optimizes its interaction with the database driver rather than repeatedly preparing the same statements. While the graphical console is excellent for ad hoc troubleshooting, scaling your monitoring strategy requires the use of the WebLogic scripting tool known as WLST. Through WLST, you can programmatically access the runtime mbeans associated with your JDBC resources, allowing you to pull granular metrics that might not be immediately visible on the main dashboard. This approach lets you write custom scripts to capture runtime attributes like the pool leakage count or cumulative wait times into a structured log format or a time series database. Furthermore, you can proactively set up diagnostic alert thresholds. For example, you could configure a script to trigger a notification when the connection pool reaches 90% of its configured maximum. Integrating this data with the standard server logs ensures you have a comprehensive audit trail, which is often the missing piece when reconstructing the timeline of a database connectivity failure. Tracking database errors within the logs is perhaps the most reliable way to perform root cause analysis after a connection timeout or a driver exception occurs. WebLogic logs provide detailed stack traces that reveal whether an error originated from a network partition, a database credential expiration, or a saturated connection pool. Monitoring these logs in real time using native tools or external log aggregators allows an administrator to distinguish between transient network blips and systemic performance issues. Remember that logs provide the narrative context that raw mbean metrics often lack, as they capture the specific exception classes and error codes reported by the JDBC driver itself. By combining quantitative data from the Monitoring tab with the qualitative insights from your server logs, you create a robust diagnostic framework. This dual-faceted approach ensures that you are not just reacting to performance degradation, but also gathering the necessary telemetry to prevent recurrence by tuning your infrastructure parameters accordingly. I will catch you in the next session. Welcome to the chapter on enterprise messaging, where we will examine the architectural foundations of the Java message service within WebLogic Server. Throughout this section, we will systematically navigate the configuration, deployment, and management of asynchronous messaging subsystems. In this lesson, we will explore the core architectural mechanics of Java Message Service, or JMS, which provides the standard framework for asynchronous communication within a WebLogic environment. At its heart, JMS decouples the producer of a message from the consumer, allowing for a highly scalable and resilient communication channel that does not require both parties to be active simultaneously. When we talk about message producers, we're referring to the clients that generate and send messages to a destination, while consumers are the clients that receive and process those messages. These participants operate within a container that abstracts away much of the underlying complexity of networking, ensuring that data is reliably transmitted according to the configured quality of service. Understanding this separation of concerns is fundamental because it dictates how we architect our middleware to handle bursts in traffic or potential outages in downstream services without losing critical business events. By mastering these mechanics, you gain the ability to build systems that are inherently more robust and easier to maintain in a production lifecycle. The logical organization of message delivery is primarily governed by the messaging model we choose, which consists of point-to-point and publish-subscribe topologies. In a point-to-point model, a message is sent to a queue, and it is intended for exactly one consumer, which prevents duplicate processing and ensures a clear distribution of labor across multiple instances. Conversely, the publish-subscribe pattern allows a publisher to send a message to a topic, which is then broadcast to all interested subscribers, making it ideal for event-driven systems where many components need to react to the same stimulus. WebLogic Server implements these via destination objects, which act as the landing zones for messages within a JMS module. Deciding between these two patterns is a classic design trade-off where you must balance the requirement for singular, serial processing against the need for broad, simultaneous notification. The architectural decision you make here will echo through your entire application performance profile, particularly regarding how load is distributed across your messaging infrastructure. Beyond the basic delivery mechanics, we must consider the non-functional requirements such as persistence, memory usage, and transactional integrity. Persistence is a critical configuration choice because it determines whether a message survives a server crash or a restart of either the WebLogic instance or the messaging subsystem itself. When we enable persistent messaging, the server writes the message to a physical storage medium, such as a file store or a database, which introduces I/O overhead that must be balanced against the necessity of data integrity. Furthermore, we must carefully manage memory allocation footprints, as queues that grow too rapidly without sufficient consumers can quickly lead to exhaustion of the Java virtual machine heap space. Transaction coordination is equally vital, as it allows us to group multiple messaging operations together such that they either all succeed or all fail, ensuring that we do not end up in a partially processed state after a system failure. These concepts form the bedrock of production-grade Java messaging, and they require a disciplined approach to configuration within the WebLogic Administrative Console. As we continue our journey, please reflect on these message patterns. I look forward to discussing persistent stores with you in the next recording. Welcome back. In this chapter, we will explore the mechanisms behind persistent stores, which are essential for ensuring data integrity and transaction persistence within the JMS subsystem. When we talk about persistent stores in the context of Oracle WebLogic Server, we are essentially discussing the physical layer where JMS messages and transaction logs are kept to ensure that an abrupt server crash does not result in the loss of critical business data. A persistent store is a built-in, high-performance storage solution that allows a WebLogic Server instance to persist data to the file system or a relational database. Choosing between a file store and a JDBC store is one of the most fundamental architectural decisions you will make as an administrator, as it directly impacts both the throughput and the reliability of your messaging infrastructure. These stores provide a durable storage format that is tightly integrated with the transaction manager, ensuring that once a message is acknowledged as persistent, it remains intact even if the local server process terminates unexpectedly. You must always consider the underlying hardware when deciding where these stores reside, particularly when dealing with high availability environments that rely on shared storage. A file store is typically the default choice for most implementations because it offers superior performance by writing directly to the disk as a sequence of files within a directory. When configuring a file store, you define a directory path that must be accessible to the server instance, and it is highly recommended that this path points to a high-speed disk subsystem to avoid I/O bottlenecks. It is important to remember that WebLogic Server manages these files by creating a collection of log files that are recycled over time, which contributes to overall system stability. You should configure the synchronous write policy carefully, as it dictates how and when the system forces data to the physical disk, balancing the trade-offs between absolute data safety and overall system latency. If you choose a configuration that disables synchronous writes, you gain speed but risk data inconsistency during a power failure, which is rarely an acceptable trade-off in production enterprise environments. Always ensure that the directory used for the store is not shared among multiple WebLogic Server instances unless you are utilizing a specialized clustered file system, as concurrent access to the same file store files by different servers will lead to catastrophic data corruption. In contrast to file stores, JDBC stores allow you to offload the responsibility of data persistence to an existing relational database management system. This approach is particularly useful in environments where storage operations must be centralized or where your data center architecture requires the use of database-level backup and recovery procedures for everything. By saving messaging records directly into relational tables, you inherit the transactional consistency and replication features provided by your database vendor, which can simplify some aspects of disaster recovery planning. Configuring a JDBC store requires an existing JDBC data source that enables the server to communicate with the target database, and you must verify that the connection pool is appropriately sized to handle the additional messaging traffic load. Keep in mind that while JDBC stores offer more flexibility for backup management, they will almost always introduce more latency than a well-tuned local file store due to the overhead of network round trips and database-level locking mechanisms. You should monitor the database performance closely when employing this method, especially if your application generates a high volume of persistent messages that could lead to table locking or transaction log contention within the database engine itself. Tuning your persistent store involves more than just selecting the storage medium. It requires an ongoing assessment of the input-output behaviors and transaction log sizes. If you find that your server is struggling under the load of persistent messaging, you may need to inspect the cache size parameters to ensure that frequently accessed messages are kept in memory, rather than forcing the server to constantly fetch them from the disk. When managing transaction logs, ensure that the log volume does not grow uncontrollably, as this can lead to disk space exhaustion or performance degradation during the server startup or recovery phases. You should also consider the impact of the synchronous write policy, specifically evaluating whether your disk subsystem supports the necessary hardware-level caches that can soften the performance impact of frequent flushing. Every configuration change should be validated through load testing, as the performance characteristics of these stores often behave differently when moving from a development environment to a production cluster. By carefully aligning the store's tuning parameters with the specific hardware, network, and database constraints of your operational environment, you will build a sufficiently robust and performant messaging layer that supports your organizational requirements. See you in the next lecture. Welcome back. In this session, we will examine the mechanics of provisioning and configuring JMS servers within a WebLogic domain. A JMS server acts as the management container for messaging resources within a WebLogic domain. When you create a JMS server, you are essentially defining a service that manages the storage and delivery of messages for a set of JMS modules and their respective destinations. From a structural perspective, these servers must be targeted to a specific WebLogic server instance or a migration target to function correctly. This targeting mechanism dictates where the messaging engine actually executes at runtime. If you target a JMS server to a cluster, you are effectively preparing it for potential cross-server migration, which is a critical consideration for high availability environments. You must ensure that the target has access to the underlying persistent store if you intend to use persistent messaging, as the store maintains the lifecycle of the messages independent of the server's immediate memory state. This procedural separation of the JMS server from the JMS module is a fundamental design choice in WebLogic to allow for granular control over resources. By decoupling the container from the message definitions, you gain the flexibility to redistribute messaging load across different hardware nodes without modifying the application code or the module definitions themselves. Proper maintenance of a JMS server requires that you pay close attention to quota management and performance thresholds. Global quota profiles allow you to define strict limits on the number of messages or the total volume of bytes that can reside within a destination at any given time. Setting a maximum byte parameter is a common defensive measure to prevent a single underperforming consumer from consuming all available heap space within the server instance. When a quota is reached, you must decide how the system handles subsequent requests, which is where custom blocking policies come into play. You can choose to block the producer, allow an exception to be thrown, or even discard the message, depending on the specific requirements of your messaging architecture. It is rarely a good idea to leave these values at their default settings in a production environment, as your specific application traffic patterns will likely demand a more tuned approach to resource saturation. Monitoring these quotas through the administration console provides the visibility necessary to adjust these thresholds before they evolve into systemic failures or service bottlenecks. Effective error handling is the backbone of a robust messaging implementation, and it starts with the configuration of your destination properties. WebLogic provides excellent support for message redirection, allowing you to move messages to an alternative destination if the initial processing fails multiple times. Expiration timeouts serve as your first line of defense against stale data, ensuring that messages do not linger in the system indefinitely if their utility is passed. When a message exceeds its expiration or reaches the maximum number of redelivery attempts, it should be routed to a dead letter queue for further analysis and manual intervention. This pattern prevents the system from getting blocked by poison pills that cannot be successfully processed by the intended consumer. By thoughtfully configuring these routing rules, you create a self-healing fabric that minimizes manual intervention and maximizes the reliability of your enterprise message flows. Take the time to map out these failure paths early in your design process to ensure that no message is ever permanently lost due to a transient error or a configuration oversight. Proceed to the next lecture. Welcome back. Today we examine the practical implementation of messaging middleware within WebLogic Server by exploring the creation and management of JMS modules. In WebLogic Server, a JMS module acts as a logical container that encapsulates the messaging resources required by your applications. Rather than configuring individual queues or factories directly at the server level, we group them into these units to simplify lifecycle management and deployment. You can think of a JMS module as a descriptor file, typically stored in the config folder, which holds the configuration data for queues, topics, and connection factories. By modularizing these resources, you gain the ability to target specific subsets of infrastructure, allowing you to deploy messaging capabilities to clusters or individual managed servers with precision. This separation of configuration from the internal server state is a fundamental architectural principle in WebLogic, ensuring that your messaging infrastructure remains portable and maintainable. When you define a module, you essentially create a blueprint for the messaging environment that the WebLogic runtime will instantiate according to your specific server targets. Once a module is established, our next priority is defining the connection factories which serve as the entry point for JMS clients. A connection factory is not merely a technical bridge. It is a configurable object that defines the quality of service for communication pipelines. Through the administration console, or WLST, you configure attributes such as load balancing, transaction timeout thresholds, and delivery modes to govern how clients interact with the messaging backplane. If you require clients to use specific compression levels or custom flow control mechanisms, you adjust these properties on the connection factory object itself. Properly tuned factories are the primary mechanism for decoupling production code from the underlying messaging topology, allowing you to scale your application infrastructure without modifying client-side logic. Every client that requests a connection from the JNDI tree receives an instance based on these definitions, which ensures consistent behavior across your entire enterprise deployment. To facilitate actual message transport, we must provision physical destination structures, which are categorized as either queues or topics. A queue provides a point-to-point messaging pattern where each message is delivered to exactly one consumer, ensuring linear task distribution and reliable processing. Conversely, a topic implements a publish-subscribe model, which is ideal for event broadcasting, where multiple subscribers receive a copy of the same message. When you create these destinations within a system module, you effectively define the logical boundaries for data exchange. It is important to note that these destinations are physically backed by a JMS server, which performs the heavy lifting regarding message persistence and runtime state management. By abstracting the logical entity of a queue from the physical JMS server, WebLogic provides the flexibility to relocate or retarget destinations without disrupting the overall messaging architecture. Refinement of your messaging behavior is accomplished through advanced configuration overrides, particularly regarding delivery policies, time-to-live thresholds, and priority settings. When a message is produced, the delivery mode, either persistent or non-persistent, dictates how the messaging subsystem treats the payload during potential server failures or restarts. You can set time-to-live thresholds to ensure that stale messages do not clutter the system, automatically discarding them after a predetermined duration. Furthermore, message priority, which ranges from 0 to 9, allows your applications to influence the order of processing for high-importance tasks versus background work. Routing properties can be further customized to govern the path messages take through the distributed destination hierarchy, ensuring efficient performance in complex cluster topologies. By systematically applying these configurations, you transition from a basic messaging setup to a highly tuned, production-ready environment that meets your specific enterprise requirements. Talk to you in our upcoming session. Welcome back to our exploration of WebLogic Server architecture. Today, we are transitioning into the implementation of distributed destinations, a critical step for building scalable messaging systems. When we discuss messaging within a clustered environment, the primary challenge is ensuring that our clients can produce and consume messages without being tightly coupled to a single physical server instance. If we rely on a single destination instance, that server becomes a single point of failure and a performance bottleneck. Uniform distributed destinations solve this by providing a unified logical interface that spans multiple member servers within a cluster. When you define a uniform distributed destination, WebLogic automatically creates a physical queue or topic instance on every JMS server that is targeted to the cluster. This abstraction layer ensures that your producer or consumer applications do not need to know the specific topology of the cluster. They simply interact with the logical name, and the infrastructure handles the distribution of messages across the available members. The load balancing of messages is fundamentally managed through properties such as the load balancing policy, which determines how producers distribute their messages across the physical destinations. By default, the system attempts to balance the load so that no individual member node is overloaded while others remain idle. However, this is not just about spreading traffic. It is about local performance optimization. In a well-tuned environment, we prefer producers to send messages to a local member whenever possible to minimize network overhead and latency. If a producer is running on a managed server that joins the cluster, it will naturally attempt to utilize the local instance of the distributed destination, effectively reducing cross-server interaction. Only when there is no reachable local destination or when specific load balancing conditions are met, does the system rely on forward routing mechanics to move messages to a remote node. For consumers, the redirection patterns are just as vital as producer behavior. WebLogic manages consumer patterns through the selection of connection factories and destination configurations that expose these messages to the application layer. When messages are consumed, you need to be aware of the trade-offs between availability and overhead. If messages are strictly pinned to a specific server, you might encounter issues where high message volume accumulates on one node while others are underutilized. By utilizing uniform distributed destinations, you allow the messaging system to balance consumption throughput effectively. If a node suddenly becomes unavailable, the persistent nature of the underlying JMS store, combined with the distributed layout, allows other cluster members to take up the slack, provided that the messaging persistence is configured correctly across the cluster. Tuning these environments requires a clear understanding of the interaction between messaging bridges, the cluster member count, and the persistence requirements of your applications. Avoid the temptation to over-engineer complex routing paths early in your deployment lifecycle. Start by establishing a clean, uniform distribution and observe the performance telemetry. If you notice specific hotspots in your messaging traffic, then, and only then, should you evaluate adjustments to custom routing or specific load balancing policies. Always keep in mind that the goal is linear scalability. Every additional server you add to the cluster should ideally increase the total messaging capacity of the system without requiring invasive changes to your existing application code or configuration. I look forward to discussing the next topic in our series when we meet again. Welcome back to our discussion on maintaining the stability of your enterprise messaging infrastructure. In this session, we will focus on the operational tracking and diagnostics required to oversee the JMS subsystems within your WebLogic environment. Monitoring the health of your messaging infrastructure is not merely about confirming that the server is running, but rather ensuring that the message flow remains uninterrupted and efficient. When you access the administration console, you gain visibility into critical statistics that define the performance of your JMS providers. For instance, Tracking the total number of current messages provides immediate insight into whether your consumers are processing data at the expected rate. Similarly, monitoring the current consumer count is essential, as a sudden dip in this value might indicate that application threads have stalled or that network connectivity between the client and the server has been severed. By looking at the total bytes pending, you can identify potential bottlenecks where the message growth is outpacing the consumption rate, often leading to heat pressure on the hosting server. Additionally, analyzing the message production rate allows you, as an administrator, to establish a baseline of normal operation, which is invaluable when you need to troubleshoot sudden latency spikes reported by end users. These metrics serve as your primary radar for detecting congestion before it results in a system-wide failure, which is the cornerstone of proactive administration. Beyond simple statistics, the administration console allows you to interact directly with the contents of your destination queues at runtime. If a specific message is consuming resources or blocking a queue because it cannot be processed, you have the authority to browse the live destination and perform manual interventions to restore order. This includes the ability to delete stalled messages that are no longer valid, or perhaps move messages to a different destination for further analysis or error handling. When viewing these queues, you should also be vigilant about the transaction states associated with the messages, as incomplete or stalled transactions often point to underlying issues with your persistent stores or database connections. This direct manipulation capability is powerful, yet it should be used with a degree of caution to avoid unintentionally disrupting the business logic that depends on the message sequence. It is quite common to find that message bottlenecks are actually caused by a single poison message that keeps failing during delivery attempts. So being able to identify and isolate these items is a critical skill for any WebLogic operator. When runtime diagnostics indicate that the system is under stress, the next logical step is to inspect the server logs for evidence of messaging engine alerts. These logs often provide the necessary context to understand why a JMS server might report an out-of-memory state or why connections are being dropped intermittently. You should look for recurring I/O exceptions, which frequently manifest when the underlying persistent storage is struggling to keep up with the write throughput of the system. A sudden surge in error signals often correlates with high load periods, which might suggest that your messaging architecture needs to be scaled horizontally, or that your persistent store needs to be relocated to faster storage media. These log files act as a narrative of the system's behavior under pressure, and learning to interpret the stack traces and error codes related to JMS will significantly reduce your mean time to resolution during incidents. Always remember that the messaging engine is highly sensitive to the stability of the underlying infrastructure, and logs often capture the symptoms of failures occurring in the broader network or operating system stack long before they appear as application errors. See you in our next session. Welcome to the chapter on securing your environment. In this section, we will dissect the Oracle WebLogic Security Framework and how it manages identity and access within your domains. The WebLogic Security Framework is designed around a modular, pluggable architecture that separates security logic from the application code itself. This abstraction is critical because it allows administrators to swap out or enhance security components without modifying the underlying server infrastructure. At the heart of this design is the security realm, which acts as a container for all security-related configurations, including users, groups, and global policies. By isolating these definitions within the realm, WebLogic ensures that security settings remain consistent and manageable across the entire domain. This modularity is not just a structural choice, but a functional necessity for enterprises that require bespoke authentication or authorization logic. When you interact with a domain, the security realm acts as the central authority that coordinates how identity is verified and how access is ultimately granted. Within every security realm, you will find a collection of specialized security providers that perform distinct roles to maintain the integrity of the environment. The authentication provider is the first point of contact, tasked with identifying users and verifying their credentials against a configured repository. Once the identity is established, the authorization layer determines whether the authenticated user has permission to perform specific actions on requested resources. To make these decisions more flexible, the role mapping provider translates organizational roles into actionable permissions, preventing the need to hard-code complex access rules directly into application code. There is also a credential mapping provider that handles the secure retrieval of credentials needed by application components to connect to external systems. Each of these components operates as a plugin, meaning you can configure custom providers alongside the default ones provided by Oracle. By default, every new WebLogic domain initializes with an embedded lightweight directory access protocol repository known as the embedded LDAP server. This directory acts as a self-contained identity store, holding information about the users and groups defined within the local domain. While this is sufficient for smaller environments or development setups, production systems often integrate external identity providers like Active Directory or Oracle Internet Directory. Regardless of the source, the security providers interact with these repositories to validate session tokens and manage security state. When a user requests access, the security stack traverses these providers in a defined sequence known as the security provider pipeline. This pipeline ensures that before any operation is finalized, every required check, from identity verification to final authorization, has been successfully validated. Beyond identity and access, the security framework includes auditing capabilities to track interactions within the domain. An auditing provider generates detailed records of events, such as login attempts, configuration changes, or unauthorized access attempts. These audit events are invaluable for compliance, as they provide a clear trail of who did what and when they did it within the server environment. You can configure these providers to write logs to specific files or even external databases depending on your governance requirements. Understanding these components in depth is essential, as the effectiveness of your domain hardening strategy depends heavily on how these providers are sequenced and configured. As we progress, you will see how these individual building blocks combine to create a resilient defensive layer around your applications. See you in the next lecture. Welcome back. In this session, we will examine the mechanisms for managing users and groups within the WebLogic security framework to ensure robust access control. When we talk about the internal security realm of WebLogic, we are fundamentally dealing with an embedded LDAP server that serves as the default identity store for our applications. Managing users and groups starts with the administrative console, where you define the identities that will interact with your secured resources. A security account consists of a username and a password, and the integrity of your environment depends heavily on enforcing strict password policies. You can configure these policies globally within the realm to dictate password length, complexity, and expiration intervals. Once an account is created, it is not particularly useful in isolation, so we assign these users to specific groups to simplify authorization. By grouping users, we can assign permissions to the group itself, which naturally inherits down to every member, creating a scalable management model. This is the cornerstone of effective security administration, allowing you to reflect organizational structures within your middleware configuration. While the default internal LDAP is often sufficient for development, enterprise environments almost always require integration with external directory services like Active Directory or Oracle Internet Directory. To connect these, we configure an authentication provider within the security realm that speaks the LDAP protocol. Connectivity requires supplying the host address, port, and the specific base DN, where the provider should anchor its search operations. Once the connection is established, WebLogic treats the external identities as valid subjects within the realm, allowing you to utilize enterprise-wide user databases without manual duplication. Because these external systems are often authoritative, we rarely perform modifications to user profiles directly from the WebLogic console. Instead, we treat the external directory as a read-only or read-write source of truth, ensuring that human resources and security teams retain centralized control over human access. When dealing with a hybrid security model where multiple authentication providers are active, the order and the JAS control flags become the primary mechanisms for interaction. The required flag dictates that the provider must execute successfully, and even if it succeeds, subsequent providers will still be called in the chain. In contrast, the requisite flag implies that if the provider succeeds, it is sufficient for the authentication process, but it must succeed if it is the first one in the chain. The sufficient flag acts as a short-circuit instrument. If the provider succeeds, no further providers are consulted, and the authentication completes immediately. If we use the optional flag, the provider's result does not impact the overall outcome unless it is the only provider configured in the chain. Balancing these flags allows you to create sophisticated authentication flows that can fail over from an internal store to an external one seamlessly. Managing operational roles is distinct from user and group management because roles are dynamic entities evaluated during request processing. While users and groups provide the identity context, roles encapsulate the functional permissions required to perform specific actions on server resources. You define these roles based on conditions, which often include checking the group membership of the authenticated principal. As you change a user's group, their effective permissions change immediately, reflecting the dynamic nature of our security architecture. This abstraction layer prevents us from having to redefine permissions every time an employee changes their department or project assignment. Maintaining clarity in your role definitions is arguably the most important task for a system administrator to minimize the risk of privilege escalation. By strictly controlling the intersection of users, groups, and roles, you maintain the fundamental tenets of the principle of least privilege. See you in the next lecture. Welcome back to our exploration of the WebLogic security model. Today, we're going to look into the configuration of security roles to manage access control across your domain. In WebLogic Server, security roles function as a layer of abstraction between the identities of your users and the resources they need to access. By assigning specific roles to users or groups, you create a flexible framework that determines what an actor is permitted to do within the container. When we talk about global roles, we're referring to those that exist at the domain level, affecting every application and administrative tool deployed within that environment. This approach is superior to hard-coding permissions directly to usernames because it allows for a decoupled architecture where permissions evolve alongside your organizational changes. As you plan your security model, think of roles as job functions rather than specific individuals, which simplifies audit requirements significantly. You will find that defining these roles early prevents the common mistake of granting overly expansive administrative rights to standard users. This configuration occurs primarily through the administration console, where you map principals such as users, groups, or even other roles to a specific role definition. The true power of this system becomes apparent when you move beyond basic membership and begin implementing declarative authorization rules and conditional expressions. Instead of allowing a role to have blanket access to a deployment target, you can craft policies that define exactly which actions are executable under which circumstances. For example, you might decide that a junior administrator should only be able to perform deployment operations during a specific maintenance window, or perhaps only when they are connecting from a designated management subnet. By using the Boolean expression language provided by the WebLogic security framework, you can inject logic that considers time of day, network origin, or specific attribute values from the user security context. This level of granularity ensures that your production environment remains protected even if credentials are misused, as the context of the request is verified against your custom policy rules. It transforms security from a static check into a dynamic enforcement mechanism that is sensitive to the operational state of your domain. Testing and managing your security hierarchy requires a disciplined approach, especially when you begin to implement role mapping overrides. WebLogic evaluates security roles in a specific sequence, and understanding how a child role might inherit or override attributes from a parent role is essential for maintaining a predictable environment. If you do not track your overlaps carefully, you risk granting unintended privileges or inadvertently locking out necessary administrative accounts. I recommend starting with the default global roles provided by WebLogic and only extending them with custom local roles when the built-in definitions are insufficient for your business requirements. When you modify access permissions for management modules or deployment targets, perform these changes against the staging domain before promoting them to production. Remember that every security policy acts as a gatekeeper. Having too many complex rules can make troubleshooting authentication issues unnecessarily difficult when things do not behave as expected. By keeping your policies as simple as possible while still meeting your security mandates, you ensure that the administration of your domain remains both secure and maintainable over the long term. We'll see you in the next lecture. Hello, and welcome back. Today, we are going to explore the mechanics of implementing SSL and TLS within a WebLogic environment. In any enterprise environment, the confidentiality and integrity of data in transit are paramount, and WebLogic Server addresses this through the implementation of the Secure Sockets Layer, or SSL, and its successor, Transport Layer Security, or TLS. When we consider the communication between a client and an administrative server, or between managed servers, we must ensure that all traffic is encrypted to prevent unauthorized eavesdropping or tampering. The protocol stack operates by establishing a handshake mechanism where the server presents its identity, typically through a digitally signed certificate, and negotiates a robust cipher suite with the client. This cipher suite defines the algorithms used for key exchange, authentication, and bulk data encryption, such as AES or RSA. If the cipher suites are not properly configured, or if the server relies on deprecated protocols like SSL-v3, the entire infrastructure becomes vulnerable to legacy exploits. Therefore, the primary task for an administrator is to configure the listeners for both HTTP and T3 protocols to specifically require secure transport variants, namely HTTPS and T3S. This configuration happens primarily within the server configuration settings, where you define the SSL port and enable the secure communication flags. Once enabled, the server will no longer listen for plain text commands on these dedicated channels, effectively forcing all internal and external traffic to wrap itself in a cryptographic layer. Managing security at the endpoint level involves more than just enabling a flag. It requires an integrated approach to trust and identity. The node manager, which acts as the cornerstone for process control and remote administration, must also participate in this secure handshake to ensure that administrative traffic cannot be intercepted. You configure the node manager to use SSL by adjusting its properties file to point toward valid key stores, which hold the server identity certificates and the necessary trust anchors. When you instantiate a managed server, the node manager utilizes these identity settings to authenticate itself against the administration server. This recursive dependency on valid certificates means that you must have a clear understanding of how the identity key store is managed and how the trust key store verifies the authenticity of peer certificates. If an administrative request originates from a source that the node manager does not trust, the connection will be dropped during the handshake phase, which is a desirable outcome for a hardened system. By enforcing these constraints, you effectively isolate the internal management traffic from the potentially hostile public-facing interfaces of your network architecture. Beyond the technical implementation, you need to understand the nuances of the handshake process, as it is often the source of most configuration errors. During the initial connection setup, the server sends its certificate to the client, which the client then validates against its internal trust store to confirm the server's identity. If you use self-signed certificates, the client will fail to verify the chain of trust unless you explicitly import the server's public certificate into the client's key store. This is particularly relevant when performing administrative tasks from command line utilities or custom scripts that interact with the WebLogic mbeans. Furthermore, you should regularly review the supported cipher suites to ensure that they align with current security standards, as performance requirements sometimes clash with the computational cost of stronger encryption. While modern hardware acceleration can mitigate some of the latency associated with heavy encryption, the choice of algorithms should always prioritize data security over raw throughput. It is a balancing act that requires a deep understanding of your specific environmental constraints and the threat vectors you are attempting to mitigate. See you in the next lecture. Hello, and welcome back. In this lesson, we will focus on the architectural mechanics of managing domain key stores to ensure secure communication within a WebLogic environment. When we discuss securing a WebLogic domain, we are primarily concerned with how the server identifies itself to clients and how it verifies the identity of the entities it communicates with. By default, WebLogic provides a demonstration key store infrastructure intended exclusively for development environments. These files are not suitable for production because they contain well-known insecure keys that anyone can replicate. To transition to a production-ready state, we must implement custom key store configurations that use industry-standard Java key store archives. This involves creating distinct repositories for identity, which houses the server's private key and public certificate, and trust, which contains the certificates of trusted certificate authorities. Moving away from the default demo files is the most critical step in hardening your domain against unauthorized interception and masquerading attempts. The process begins by utilizing the Java Key Tool utility, a standard tool bundled with the JDK that provides the necessary primitives for cryptographic management. You will use this tool to generate a new key pair for your server instance, ensuring that you choose an appropriate key algorithm and length that aligns with your organization's security policy. Once the key pair is generated within a key store file, the next requirement is to obtain a signed certificate. You perform this by generating a certificate signing request, or CSR, which effectively asks a trusted certificate authority to vouch for your server's identity. This interaction results in an authorized certificate that you must then import back into your key store to finalize the chain of trust. Failing to properly handle the import process often leads to SSL handshake errors that can be notoriously difficult to debug if you lack an understanding of certificate chains. After your key store files are prepared on the file system, you must instruct WebLogic to utilize them instead of the default demo configuration. This is accomplished through the WebLogic Administrative Console within the Key Stores tab of the server's configuration settings. You are required to specify whether you are using the default Java key store type or an alternative provider, the full file system path to your custom identity and trust files, and the necessary passphrases to unlock these archives. It is important to remember that these passwords are stored in the domain configuration, so they should be managed with the same level of care as other sensitive credentials. Once you update these fields and save your changes, the changes will typically require a server restart to take effect, as the cryptographic context is initialized during the server boot cycle. When configuring the custom trust key store, you must ensure that it contains the root certificates of any certificate authority you intend to trust. This is the mechanism that prevents man-in-the-middle attacks where an intruder might attempt to present an illegitimate certificate during a connection attempt. If your internal applications communicate with other secure services, the trust key store must include the public certificates of those services if they are signed by a private or internal CA. You might find yourself managing multiple key stores for different roles within a cluster, but the fundamental principle remains the same. Consistency across the domain is key here, as mismatched certificates or missing root certificates in the trust store are frequent causes of deployment failures when attempting to establish secure outbound connections to databases or external web services. See you in the next lecture. Welcome to the final section of our security module, where we focus on auditing domain activity and interpreting security logs to maintain system integrity. In this session, we will examine how to track environment changes and unauthorized access attempts through the WebLogic auditing provider. Effective security in a WebLogic environment requires more than just authentication mechanisms. It necessitates a robust trail of what happens within the domain. The WebLogic auditing provider serves as the primary mechanism for capturing structural system events, security check results, and administrative actions. By default, this provider can be configured to record significant lifecycle events, such as when a user is added to a group or when a service target is modified. From an architectural perspective, this isn't just about logging text to a file. It is a structured system that integrates with the security framework to ensure that sensitive operations are verifiable. When you configure the auditor, you essentially define an audit scope that determines which events warrant a registered entry. This becomes vital when you need to recreate the sequence of operations that preceded a configuration failure or a security breach within your production environment. Navigating the security log file system is often the first step in diagnosing configuration issues or identifying malicious intent. WebLogic generates specialized logs that record access violation signatures, such as systematic authentication failures that might indicate a brute force attempt. Because security logs tend to rotate, establishing a consistent pattern of log collection is necessary to ensure that you are not losing forensic data during periods of high activity. When you examine these logs, you should look for patterns in the timestamps and the specific service IDs involved, as this helps differentiate between legitimate administrative routine and potential environment modification. Identifying an authentication failure is straightforward, but correlating that failure with other administrative anomalies requires a systematic approach to log filtering. By keeping a sharp eye on these signatures, you maintain a reactive barrier that is just as important as your proactive preventive measures. Hardening administrative tools is a critical countermeasure against unauthorized access, and this involves more than just changing default passwords. One often overlooked step is disabling public help flags or unnecessary management consoles that expose system metadata to unauthenticated users. Additionally, configuring server lock tracking is a best practice that prevents multiple administrators from unintentionally overriding each other's configurations, which maintains the integrity of the domain state. When you implement these hardening practices, You are reducing the attack surface by ensuring that only authorized operations proceed through the intended management channels. The combination of audit providers, active log monitoring, and hardened interfaces forms a defense in-depth strategy, which is the gold standard for maintaining a secure WebLogic server installation. Consistent audits and vigilant log management allow you to act with confidence, knowing that your domain's configuration history is both transparent and protected. See you in our next session. Welcome to this final session, where we will consolidate everything you have learned to ensure you are fully prepared for the 1z0-133 certification exam. We will cover final strategies and a comprehensive review of the core domains. Achieving the Oracle WebLogic Server 12c Administrator certification requires more than just memorizing configuration steps. It demands a deep understanding of the underlying architectural principles. You must be able to distinguish between static and dynamic clustering while understanding the specific use cases for each topology. When you analyze a scenario regarding system architecture, consider the trade-offs between manageability and high availability. Remember that the node manager is the fundamental utility for lifecycle management across distributed environments. Yet its configuration often causes confusion during exams. Your ability to troubleshoot the communication between the administration server and managed servers is a frequent target for examination questions. Think about how the different network channels interact with request routing and how that relates to the overall health of your domain. You should feel comfortable explaining how domain-wide configuration changes propagate through the infrastructure and how that differs from localized server modifications. If you can explain the mechanics of a rolling upgrade or a server restart sequence, you are likely in a good position to handle the more complex deployment questions that rely on these core concepts. In the area of persistent configuration, the distinction between JDBC data source types is critical, especially when differentiating between generic, multi, and grid-linked data sources. Many questions focus on the configuration of connection pools and the specific parameters that define their behavior under high load. Pay close attention to how WebLogic utilizes the JDBC driver to handle connection requests, and when you might need to tune these properties to prevent resource starvation. Similarly, Java message service provisioning requires a disciplined approach, specifically regarding the creation of persistent stores and distributed destinations. You need to understand how the JMS server manages messages and how that interacts with the underlying file or JDBC storage mechanisms. If you encounter an exam question regarding messaging, map the components first, starting from the message destination through the JMS module and eventually into the backing persistent store. Understanding the hierarchy of these objects is essential for correctly identifying the root cause of service failure scenarios in the exam environment. Security hardening is another domain where precision is required, particularly with SSL/TLS implementation and key store management. You should be able to walk through the complete chain of trust, from the root certificate down to the identity and trust key stores configured at the domain level. Do not overlook the administrative aspects of security, including the distinction between security roles and groups, as this is often tested in authorization scenarios. When thinking about auditing, consider how log files are generated and where they are stored, as this relates directly to your ability to perform incident response. A common pitfall is misunderstanding the scope of an audit policy. Always remember that auditing is granular and must be explicitly configured to capture the correct events. By internalizing these security workflows, you can approach the more abstract security policy questions with a clearer understanding of how the WebLogic security provider framework actually executes requests. Regarding your exam strategy, time management is your most valuable asset during the actual testing process. You will face a mixture of straightforward knowledge-based questions and complex, multi-choice scenarios that require careful analysis. I suggest reading the scenario requirements twice before looking at the provided options, as distractors are specifically designed to sound plausible based on common misconfigurations. Eliminate the obviously incorrect answers first, then focus on the structural nuances of the remaining choices to identify the most accurate solution. If you encounter a particularly difficult question, do not spend excessive time dwelling on it. Flag it for review and move on to ensure you finish all items in the allotted time. Your goal is to maximize your points by securing the easy wins early and leaving yourself sufficient time to perform a final review of your tentative answers. Create a mental checklist for each diagnostic domain, specifically focusing on the lifecycle and configuration steps we discussed throughout this course. For example, when you see a question about deployment failures, instinctively run through the staging modes and deployment plan requirements in your mind. If the question asks about cluster communication, immediately verify which network channel or load balancing algorithm is being applied to the scenario. Using these mnemonic associations will help you retrieve the necessary technical details quickly under the pressure of the exam. Finally, trust in the foundation you have built, as it is grounded in the standard administration practices that Oracle expects all certified professionals to demonstrate. You have invested the necessary effort to understand how the components piece together, and that holistic view is exactly what this exam aims to measure. Good luck with your final preparations and success on your certification exam.